Okay, is everyone settled? Good morning, everyone, and welcome to the Transparency.dev Summit. I'm Tracy Miranda, so if you're here, you probably received an email from me at some point. So welcome, and thank you all for making the trip. I know we've got folks from a lot of different places. We've got Netherlands and Switzerland and Portugal and Canada, woo, shout out, the US, and even some folks from Australia. So thank you very much for taking some time from your busy schedules to be here with the community. I know you're all keen to hear Al speak, but I do have a few housekeeping and welcome things to go through, so we will get to that. Yeah, just a little bit about the conference. So Transparency.dev Summit was conceived by the Trust Fabric team, and they've been to many amazing events like CT Days and CATS. Is anyone here who was at the last CATS? Yeah, good set of folks. But the idea here was to really put real-world transparency systems front and center, and also seeing the success of CT has led to so many other places where transparency has been adopted. Give some space for those emerging communities to get together, meet each other, and see what it takes to get to the next steps. And with that in mind, there were these 5 key pillars that the team identified that they really wanted to focus on at this event. So you will see specific sessions dedicated to witnessing. We have a whole set of talks and a discussion space, which will happen on Friday, so everyone's invited to that. On Thursday afternoon, we have some breakouts, one for certificate transparency, another for binary transparency, and a smaller but fully formed one for key transparency as well. So you do have to pick your room, but yeah, looking forward to some really good discussions in those spaces. And then when it comes to transparency futures, I think we'll see a little of that sprinkled throughout the schedule about what's coming next, where are we all going as a community. Yesterday at dinner, I had a chance to meet some other attendees, and I think it was Justin. He made a comment about, like, when is it you're in a room where you don't have to explain what certificate transparency is, or it's really easy to explain to people what you do. So yeah, really happy to have this great set of folks together who can yeah, just advance things. All right. All right, some housekeeping. I've worked in open source for a long time, but I'm new to this community. Everyone has been amazingly friendly and open, which is nice. We'd like to keep it that way. So we do have a code of conduct I'll ask everybody to take a look at, but the TLDR is just be excellent. If you do have any concerns, please reach out to myself or Patrick Flynn, he's going to give a wave there, or any member of the Trust Fabric team, and we'll be happy to help. Speaking of which, these are the Trust Fabric team who will be your hosts today. So feel free to find anybody if you need anything, not just code of conduct, but anything we can help with. I will say that this is a working Google Office, so it might be tricky for folks to sort of go back down or wander around. So you will need someone with a Google badge if you want to access the elevators or if you need to come back in. So do give us a shout or ping anyone you see with the Google badge should be able to help you. And also for the Thursday event, we'll help you get up to the space. And while the Trust Fabric team conceived and developed the ideas, we couldn't have done it with the community. So we had a lot of awesome folks who were part of the planning committee. So I want to give a shout out to all these folks who gave some really amazing feedback and really helped shape the program and made sure we had live streaming. So hello, everybody at home. So thank you very much to all of you. And well, actually, I'll go for a round of applause at this stage. Thank you. Okay, other housekeeping, if you haven't already discovered it, these are the Wi-Fi you can use Alphabet Guest in this room. Google Guest if you're down in reception. No password required. And yes, as mentioned, we are live streaming all the talks and the lightning talks. The breakout rooms and discussion spaces will not be recorded. They will not be live streamed. If there's any speakers who prefer not to have their talks recorded or live streamed, please let me know. And also attendees, if you want to stay to the edges of the room and you can avoid being on the stream if you prefer that too. Otherwise, please follow the YouTube channel here, and that's where you'll find the talks when they're posted, as well as the different streams for each individual day. Okay, quick glance at the schedule today. We're going to kick off with the keynote in a minute, and then we'll have some talks. Each day, we'll be having a morning break, lunch, and an afternoon break, and we'll have some snacks, refreshments, lunch, all in the back of the room here, so keep you fed, watered, and coffeed if you partake. So yep, feel free to keep the conversations going. Follow the schedule online for the latest on the talks. We are tweaking it as we go. And I want to flag a couple of things. You'll hear more about this later on in the conference, but I want to let you know we'll have some free lightning slots for anyone who's come along and would love to speak to the audience. Ideally, you're not already giving a talk, but you have a different topic or something that you haven't seen covered and you'd like to bring that up. I'll be giving more details about how you can sign up for Lightning Talk, but come ask me if you have any questions. You may have seen also on Friday afternoon, we're looking to maybe get away from the speaking and get the laptops out and start working on stuff, get deep dives. So we have some birds of a feather session. So again, we really want to know, are there specific topics people are interested in discussing, questions they want answered, or some code they want to work on. We'll set up a sign-up sheet as well where you can let us know things you're interested in, and if we can get enough folks together, yeah, we can designate some space for that to happen. So again, watch this space. We'll share more as we go. And yeah, I will shout out that we do have a social event this evening, which I'd love if you could all join us at. We're going to take the chance to leave the office and go enjoy the best of British with some darts. The Trust Fabric team have tried this out, and they know it's a lot of fun. If you want to play with Roger, he's very good. I recommend. It's very handy. So we'll be finishing all the talks by 5 today, and the event starts at 6, so we'll give folks some time if they want to drop off bags. There's also a lovely walk you can do which goes along the Regent Canal towpath for some of it, and we might self-organize. If there's enough folks who are interested in doing it, we might organize a group who can all go down together. And yeah, I think the weather is looking good, so fingers crossed it stays dry. We do have a waiver sheet as well, which we'll be asking folks to sign. But yeah, we'll have those out, and you can either do it beforehand or once you get there. Okay, and those are all the announcements. So yeah, thanks again, everyone who could join, and thank you very much to all the speakers. But I'd also like to give a big thank you to our hosts, Google, for providing this lovely space, all the food we're going to have, and yeah, just bringing the community together. Okay, and with that, okay, so why don't I get you to come set up, Al, and I will intro you. So while Al is setting up, I'm pleased to introduce our keynote speaker is Al Cutter, and I've had the pleasure to work with Al just over the last few months, and it was soon after I joined, started working with the Transparency Summit, and everyone pointed out in Slack how Al had been one of the winners of the Leveraging Prize, which was like something I'd never heard of, but when you see all the people he's in esteemed company with, I think it really hit home the impact transparency and certificate transparency has had. But yeah, it's always a great person to talk to and an inspiration. So I'm very much looking forward to this talk. So please give a round of applause to Al Qatar.
Okay then, well, welcome to the inaugural Transparency.dev Summit. If anybody doesn't know me, I don't know if that's the case or not, but everyone doesn't know me, I'm Al. I'm the tech lead for Trust Fabric here at Google. I don't mind admitting that this is a pretty exciting day. We've wanted to have an event like this for a very, very, very long time. We have had many talks about transparency, certificate transparency at various conferences over the years. Last year we had CATS, which was fantastic, and now here we all are together for our 3-day summit for transparency practitioners, which I think is fantastic. If I look back at sort of the CT ecosystem and how it evolved, the sense of community that we had that grew from those CT days, the communications, the sort of the tightness that we had was invaluable, I think, in having it become the reality that it is today. And so I hope that we will see a similar thing happening here too. So the schedule, echoing what Tracy said, looks fantastic. I'm super excited about it. There's such a wide range of talks across many aspects of transparency. We've sort of grown from CT now to many other applications, which is super exciting, and I'm very much looking forward to hear what folks have to say. I hope you all enjoy it as much as I will. And I think, again, just with that nod back to community, while you're here, we've got a bunch of time together. While you're here, please do take the opportunity to go and find folks that you don't know yet and say hello. Build those connections, because this is important. This is the way that stuff gets done. If you don't know who to talk to, come and talk to me, and I will introduce you to other people. If you have any problems, you're stuck, you're lost, whatever it is, then we're all friends here. So come and find me or one of the other Trust Fabric team. In fact, actually, Trust Fabric team, can you stick your hands in the air and put your biggest, warmest, welcoming smiles on? So these folks are all here for you. We're at your disposal, so find us if you need us. Right, so with that, I'll keep riffing on this community theme. So for millennia, humans have used rituals like gathering around fires to tell stories and this sorts of stuff. It's how we pass down knowledge, how we form community, form bonds, and all the rest of it. They wouldn't let me have a fire, not after the last time, but we do have our sort of ritual story that gets told at every one of these events, and this is sort of how CT came to be. So this time it's my turn to tell the story. So the year is 2010. That's it. Nothing happened. It's very boring. Occasionally you might get someone wearing a tinfoil hat coming along and saying like, oh man, the man reads your browser when you go to Yahoo, but Snowden hadn't happened, and so nobody really pays any attention to it. Then the next year, and this happens, once upon a time, Did You Know Tar was a Dutch CA. It gets pwned. Its private key material extracted and turns up on the border gateway routers of Iran, where it sits, and man in the middle is all of the traffic from the folks that are inside Iran going out to places like Hotmail, Google, and indeed Yahoo. So there are predictable results that come from this. It's slightly unfortunate, not least of all, because I have to go back and find the person with the tinfoil hat and apologize. But it is mildly disastrous that this has happened. And so, we think that somebody really should do something. So heads get together, we'll start thinking about it a little bit. Wouldn't it be good if certificates couldn't be issued without anybody knowing about it? Like specifically without the domain owner knowing about it. That seems like it might be quite a nice thing to have. And it would be a little bit like shining light into dark corners so you can see what's going on. And you know what they say, right? Like sunlight is great at cleansing and killing off infections. And so someones do something, and the something is draft lorry PKI sunlight. Time passes, and draft lorry PKI sunlight turns into RFC 6962. The CT team at Google is furiously coding away to write the first CT log implementation, in C++ for some reason. I guess that's what we did then. So now we have, Merkle trees. Well, we had Merkle trees for a while, but now we have logs built on Merkle trees. Time goes on, and some CAs become early adopters because they realize that this is important, right? Like, they're in the industry of trust, and so this is a way to improve and sort of build on trust. And so they're like, yeah, we like this. Other CAs were a little more hesitant, so there might be a little bit of back and forth that went on, a bit of negotiation. But it sort of starts to happen. Folks start writing clients to have a look at the things that are in the logs and sort of other sort of related to tooling. And then over the next couple of years, we start to see that an ecosystem forms. A large browser rocks up and starts requiring CT for a subset of certificates. A bit later on, another one comes along and does the same. Monitors appear, and this is the year that the venerable crt.sh rocks up. Where is he? There he is. So the ecosystem sort of continues developing and maturing, and you know what? It turns out that it works, and together we catch tens of thousands of misissuances, we catch backdated certificates, weak keys, baseline requirement violations, and all the rest of it. And where it's appropriate, then action's taken. Appropriate corrective action is taken to ensure the safety and integrity of the TLS ecosystem, because it turns out it's quite important and we all rely on it. So, as Tracy sort of said earlier, in fact, CT works well enough that this year it wins the Levchin Prize at Real World Crypto. So I want to take a minute just to say that if you, and I know that many of you were, if you were involved in turning CT into the success that it was in any way, however small it was, then I ask you to see yourselves reflected in this as well. This is a prize for all of us, because we all pulled together to make CT work for the benefit of everybody else. Back to the story. So obviously this isn't the end of CT or transparency in general. We see new experiments, new green shoots growing. The CT static API, for example, was one of them, where we've taken the lessons that we've all learned over the last decade of how you build transparency systems, how you operate transparency systems, and feeding that back in to the CT ecosystem design. So it evolves and it grows. Obviously, over a similar time period, we see the same sort of evolution and growth of types and intensities of malicious activities that are outside the scope of CT. There are some here. I'm sure that you can name many, many more too. So I guess it's inevitable that with the success of the application of CT to the set of problems that it is looking to solve, we see folks wanting to apply similar properties and principles to some of these problems. So, for example, we have binary transparency, which is maybe a bit of an umbrella term, but we see that coming to answer the question of how do we safely consume and publish binary-like things. We have key transparency. How do we safely manage, share, update our keys so that we can have nice things like end-to-end encryption? We have signature transparency. How do we safely use and manage our signing keys so that we know if they're being misused? Firmware transparency. Can we sort of push these benefits further down the stack? We've got it at TLS. We're starting to see it at sort of application and binary level now. Can we go further down? Can we have it at the operating system? Can we push it down into firmware, down into hardware? What does that mean? And obviously AI transparency as well. It's I've got to say something about AI, but it is like, how do we safely sort of create and publish and consume AI models and their outputs, right? So I sort of said earlier on that we've got a wide range of talks, and we're going to hear something about actually all of these areas over the next 3 days. So it's fantastic. We've got binary transparency breakout on Thursday. We've got William Woodruff talking about transparency and PyPy. Key transparency breakout on Friday with folks from Proton and Meta and indeed Apple. We have signature transparency talks from Rasmus and our very own Hayden. Firmware transparency, I'll be back a bit later on with Martin to talk about that, because I like that very much. And on AI, we have Mihai telling us about that on Friday morning. So if these are our verticals, then the tooling that we have to build these things are horizontals. And obviously, similarly, there's an evolutionary growth of those over the time that we've been using them to become more general purpose and hopefully cheaper and easier to run too. So if I sort of go down memory lane for a little bit and think back to 2013, we had that original C++ CT log, which is quite quaint. There were only 2 million certificates in the world back then, so everything went into memory because you could do that sort of thing. Now we're at like 2 billion certificates every year, which is an incredible amount of growth. So clearly that infrastructure wasn't going to scale to where we are now. So 2016, we started with Trillian. We wanted to decouple the C from the T to try to encourage these sort of other applications of transparency to happen. And I think I'd argue that it worked reasonably well. Trillian has underpinned CT until today, but it also sits underneath the Go SumDB. It sits underneath Sigstore, and then it was used in sort of other less talked about places. It's used, for example, in production change auditing at a payments processor, and it was even used for like actual food supply chain and fraud work some time ago. All of these applications are, fairly large scale, and so we did start to think about, well, what would the other end of the scale look like? If you only had something that you needed to commit to in a log, once in a while, what might tooling look like for that? So in 2021, we experimented with something called serverless, which was basically Unix tools for logs, where you manage those logs as a set of files in a file system. And then more recently, we see Sunlight and Static CT API coming to sort of put many of the lessons that we learned over this time back into CT, as I said before. And so we, again, sort of trying to separate or decouple the C and the T. We've been working on Trillian Tessera that we'll talk about a bit later on. And again, that's something that can be used to implement Static CT API, but also it brings much of those lessons that we've learned to the other ecosystems, which should probably adopt them too. So the upshot of all of this evolution, sorry, I went on at length there, is that logs are now boring and commodity. Like, obviously, logs are not boring. Logs are super exciting, and I love them very much. But with Sunlight and Tessera, from an implementation and an operations point of view, I think we can start to now consider this part of the infrastructure somewhat boring and turnkey, which is important. We've also seen sort of the evolution of the protocols and formats that we've used over time. So back when 6962 was the only real sort of instantiation of transparency, it would be normal that everybody would copy, the STH and proof formats and all the rest of it from there. And then over time, we've seen them sort of become a bit more general purpose and reusable. So I think it's worth noting that these formats that I'm referencing here, the generic checkbook, the witnessing stuff, tiles, all the rest of it, the way these happened were through basically more experiments, right? Someone trying something, let's see how it works. Does it stick? Do people like it? Oh, they do. And then from there, they landed on the C2SP community specs repo. But this is, again, like why we're all here, right? To sort of make these connections and be able to work together, experiment together, and form consensus and move forward with new and exciting things. So with these new sort of more common and generic formats and protocols, we also start to see interoperability beyond the ecosystem level, so between ecosystems. And this is interesting because now we start to get other shared horizontal services, such as witnessing, for example, which most ecosystems are going to need. We also get a bit more code reuse, which is nice because nobody likes to have to keep writing the same things and maintaining all the same things. The other thing that's changed and evolved is sort of what we consider to be necessary for trust. It's a bit different to the other slides, but it's fun. I thought it was fun. So, back in the day, we would make things available on the internet, and you might be, I'm going to show my age here, but you might be using your FTP client to download something from Woo Archive or 2Cows for the younger kids. And then, you're downloading this over your modem, and your mum's downstairs, and she picks up the handset because she wants to phone Auntie Vera. Oh no, now it's all gone wrong. Did you get the file? I don't know. So we solved that by having MD5 sums that we just would plop next to the file, and we can download it. Because what we were worried about then was integrity. Time passes, and this is no longer enough. And we start to be concerned a little bit with authenticity as well. So we start replacing MD5 sums with signatures. I'd argue that the meaning of these signatures was never particularly clear. But certainly it means that someone had access to a private key and the thing, and then they did a thing, and now you have a signature. But you know, a lot more meaning was implied on those things and never really sort of clarified, which was problematic. And so from there, we started to want to have some notion of accountability. So, you know, we started logging things. But here's the thing. I can't believe Al's saying this. Putting things in logs doesn't matter. I'm going to get fired. What is that matters is discoverability and verifying the claims of things in log. So discoverability, I mean that we are all seeing the same set or list of things, however you want to phrase it. And you know, witnessing is an important part of this. We don't want split view attacks. Verifying claims, well, so I sort of talked about what the signatures mean. When we start to think about transparency and having claims in logs, it forces us to be very explicit about what the signature means. So we can add a new thing to our list of the evolution of the bar for trust. Actually, what we want is not logging, what we want is transparency. So this means that someone's accountable for the thing. That probably means that it's signed, but it also means that they've made some statements about the thing. You know, it's not malicious, or it's reproducibly built from this git commit using this toolchain and resulting in this hash of a binary or what have you. There could be, you know, many different types of claims. But the important thing about these claims is that they need to be falsifiable. There's no good me just going up and saying, no, trust me, bro, this binary's fine. Like, somebody else needs to be able to call me out if I'm lying. So not only do they have to be falsifiable, but they have to be entities that are actively trying to falsify these claims and call folks out when they make bad claims. And lastly, they need to be discoverable so that we can be sure that those folks do see all of the claims and will try to falsify them. So we're going to hear more about this sort of closing the loop of ecosystems from Fillipo, who's down there furiously writing his talk a bit later on today. But for now, I think I will just leave you with this. So our ecosystems that we love and that we're super invested in, they need us, right? So if you are a tooling person, please consider using the C2SP specs that I mentioned earlier on for your formats and your protocols. If you think that they don't work for you or they can't work for you, then let's figure out why. And you know, what do we do to change them so that they do work for you? And an easy way to do this is to use Trillian Tessera. If you are doing ecosystem design, then ensure that your design is closed, right? So sort of, as I said earlier on, what are you putting into your logs and why? Do they represent claims? Are those claims falsifiable? Do you have verifiers that are able to falsify them, and do they exist? And at least for the sort of the discoverability part of this, the C2SP specs can help with that too. And the last point is that we need to demand transparency, right? It's not enough for us to meet here and to invent new things, new protocols, new systems. We also need to make sure that we're creating and signaling demand for the systems which embody these principles, because that ultimately is what's going to sort of help these green shoots of growth and evolution continue to grow and receive, you know, the sunlight and the sustenance that they need, because ultimately somebody's paying for all of this. So continue to raise your expectations, as we did from MD5 sums, which were the bee's knees once upon a time, now to transparency. Let's keep ratcheting it up. Ask for transparency for your dependencies, your operating system vendors, your cloud providers, your hardware vendors, like basically anywhere that you think that it's going to sort of reduce the need for blind trust and improve security. So that's the end of my fireside tale. Thank you for listening. Thank you very much for coming and being here over the next 3 days, and enjoy your summit. If there are questions, I'm happy to answer some. Otherwise, can just hang out together and be cool.
Are you at liberty to tell?
Will you repeat the question?
Are you at liberty to tell us more about the food supply chain thing?
Am I at liberty to say more about the food supply chain? Well, it was PwC, and it was sort of APAC region, and what they were worried about was mainly fraud in the beef and wine supply chains. So there was some sort of interesting adjacent technology that they did as well with unforgeable watermarks that wouldn't kill you if you ate them. So you know, it's just like, yeah. Yogesh.
Sorry, can I get
You presented an excellent past evolution of transparency back from 2013. Going forward, do you have any kind of thought or ideas on how it would look like in 5 years or some roadmap in that direction?
We'll all be done in 5 years. Everything's going to be super tight and it's going to be amazing. No, I don't know. I'm not. That's quite a long way to look into the future. I think, you know, what we're going to see next, I hope, is logs looking more or less the same shape, which makes it easier to use each of them. The cost of logs and log operation coming down, which removes a lot of the hesitancy or barriers to adopting this technology. If you just have to run a tool to magically have a log next to whatever it is that you're offering over the internet, I think that'll make life a lot easier. I would very much like to see, you know, this sort of horizontal shared witnessing network, because, you know, every ecosystem is going to have to solve split view attacks somewhere or another. So if we can have a common system that does that, then that's great. That's as far as I'll go for the minute. Ask me later in the pub. No more? All right, cool. Well, thank you.
Great, thank you very much. Can I get Rasmus? Come get set up, please. I have to say, whenever you have a slide and it says AI model transparency, I now read it as OWL model transparency. So.
I do not want an OWL model.
All right, cool. Hi everyone, I'm Rasmus from Glasklar Teknik in Sweden, and this is me jumping straight into the presentation. I'm going to tell you about what Sigsum is and how we can use it for your application. So for short, Sigsum is a free and open source software project, and we provide a building block where you can discover which digital signatures are out there for what cryptographic signing keys. And the way that we approach this is by introducing a public append-only log for this building block. And basically what you get as a property here is transparent key usage. So every time you use your signing key, there's going to be a signature that's pushed into this log. Why is this an interesting problem to solve? So suppose you have one of these signing keys. My question to you is, how would you know if it has been compromised? So say the attacker has been able to somehow copy your key and then run away with it. Say they have, like, for a very brief moment, signing oracle access to your key. How would you know if they sign a malicious message and then they serve that to some user? Most likely you wouldn't know about this happening. And this is the problem that Sigsum is trying to solve. Which digital signatures are out there for what cryptographic public keys? The other thing that's interesting about Sigsum is that if we can start agreeing about what are the different signatures that are out there for different keys, we can also start talking about the data that you are signing things with. So it's the data as expected. So take, for example, a software developer, and you are signing some release. Now we can back up a claim like you're always going to put your signed binary on your GitHub release page, and it's always going to correspond to the Git tag. So you have those falsifiable claims, as Al was talking about, and you can now back it up because you know what are the messages out there that have been signed. So you have a concise history of this. So these are problems that Sigsum is solving. The project is funded by Mullvad VPN, and most of the development is led and done by Glasklar Teknik, which is a sibling company that started around 2 years ago. Going even further back in history, Sigsum was part of the System Transparency project. So this is something that Mullvad founded in 2019, and I remember when I met Frederick at a conference in 2019 in Stockholm, and he told me about how he wanted to basically prove to third parties what image is booting on a particular server. And one part of this design was to have a signature transparency log. And I remember for the first revision, then the idea was to piggyback on the existing certificate transparency infrastructure. And then I talked to Frederick. And then we agreed that it would be a much better idea to not do that and instead design a much neater log, which actually gets you a lot further and without any of the kind of hacking and piggybacking onto things. So we started out trying to develop this system transparency log together, Frederick and I, in 2020 in October. And I've been iterating for this for quite some time. So at some point we realized this building block is more interesting than just for system transparency. So then we rebranded this as Sigsum. And then as we've been iterating, we've been collaborating with a lot of different community members. Like we've been talking a lot with the Trust Fabric team, like Al and Martin. We've been talking a lot with Fillipo, which is also a contributor of the project. And if I had to put out something which is I think interesting to look back on, is a bit how we've been navigating the design space for when you're designing a public log. And I think if you do design a public log, here are some of the design parameters that I think you would like to have some explicit choices on. And Sigsum has obviously some choices for these, and I'm gonna get back to this table a bit later in the presentation. All right, so suppose you want to use Sigsum. Sounds great to know what is happening with your signing keys. Here is kind of the setting that we're trying to plug into. So we're going to assume that you already have some data and you want to be signing this data. We're going to assume that you already have a distribution mechanism for this. So you already have the way to get the data and the signature to the user. We're not solving data distribution for you. So maybe you're doing this on a GitHub release page, maybe you're doing this on a web server, whatever works for you. And we're also going to assume that the setting here, the user knows the public key. So we're also not going to solve a key distribution for you. So somehow the user is able to, run the right verification software with the right public key. If your setting looks like that, or if it could look like that, great. Sigsum could be a good fit for you. The the attacker we have in mind here is one that is able to control this signer, so it can make any signature it wants. It can also control the distribution mechanism. So maybe they run the distribution mechanism, maybe they can do man-in-the-middle attacks. Pretty powerful attacker. The only limitation that we have is that the attacker is risk-averse. So they would really like to do this, tampering and signing, but if they get detected, it's like, nah. And this is like the typical transparency log setting where you want to detect things, and because you can detect them, you can also deter them from happening in the first place. So the goal here is simply we want to detect if the attacker is doing these malicious signatures, and hopefully that will cause some deterrence. So as an overview, we still have in the Sigsum system this signer and the user and this assumed distribution mechanism. We're introducing 3 additional parties. So one is, of course, the public append-only log. So this is basically an RFC 6962 Merkle tree, which you're all familiar with. And what it stores is signatures so that we can discover them. We're also introducing a monitor. So now we can enumerate this log and see for yourself what are the different different signatures that are out there for different public keys. And then in order to solve this split view problem that Al was talking about earlier, and also actually to solve freshness for the monitor, we have another party called a witness. And this is going to help us out tremendously. And this is those C2SP specs that Al was talking about earlier. So let me talk about each of these parties in a little bit more detail. Before I do, security assumption. Threshold of those witnesses are of course, not compromised by the attacker, but the attacker is allowed to run some of them, and the attacker is allowed to run the log. All right, so looking at the user, suppose you're not using Sigsum, then this is kind of the setting where we're starting. You have a distribution mechanism, somehow you get the data, you get the signature, you verify it with the public key. This is all happening offline. So this is either gonna pass or it's gonna fail. If you add Sigsum, it looks almost identical actually. So you still have the distribution mechanism, the user. The only thing that changed here is instead of having a signature, we have a proof. And instead of having a public key, we have something called a trust policy. Now the public key and the signature actually haven't gone anywhere. So we're just going to have the signer's public key. It's going to be encoded in the trust policy. And the signature is going to be encoded in the proof. Then what we're also going to have in this trust policy is basically what is the identity of the logs in the system, what is the identity of the witnesses in the system, and how many of those witnesses are you going to require in order to consider this basically a secure system. And then for the proof, the signature is still in there, and then we have some other cryptographic details, which is going to convince you that this is a transparent signature. And my collaborator, Fillipo, usually likes to call this a spicy signature. I will just stick with proof for now. I'm sorry. But yeah, so the property you get here, you had offline verification before, and you still have that after, and this is going to make it so much easier to integrate this with your application. So if you want to talk about why that is a nice thing to have, we can do that more in the breakout. But basically, reactive auditing and gossip is messy. Looking at the monitor, so great, we are now able to verify and enforce the logging. Now we also want to start detecting stuff. So without Sigsum, I put the sad face because we don't have a monitor. If you add Sigsum, then you can start enumerating this log and see for yourself what are the signatures that are out there for the public keys that you care about in your trust policy. And for this monitor to know that it's seeing the same signature that the users are accepting, it's also going to be configured with what are the logs in the system, what are the witnesses in the system, and then it's going to get this checkpoint that I was talking about. And this is going to be basically the state of the log, and then those witnesses claims that this is actually an append-only log and it's fresh and you're seeing the same thing as everyone else. So this is what you get with Sigsum. You get to see all of those signatures. You can discover them and you can start doing something about it if it's an unwanted signature. So what you can also do with Sigsum is that you can start pulling the data if you know where it exists. So if you know that there's a claim that you're only signing binaries and you're putting them on your release space, now you can start putting the pieces together and see, well, are actually all of the signed binaries on the release page? Are they actually corresponding to these Git tags? And this is kind of how you can close the loop and start doing things where a third party can assess your claims rather than you just being able to know what happened with your public keys. All right, looking at the signer perspective here. So before, you could always sign something, and that's quite effortless. And this is part of the problem, right? Because if the attacker kind of takes your keys and runs with it, then it can start signing things. So here, some things ought to change a little bit. So what's going to happen is that when you want to sign something, you're going to sign a checksum, and you're going to put this signed checksum into the log. Then after a few API calls, you're going to get back this proof that we were talking about earlier, which is basically just the signature, and it's encoded as a proof, and you're also going to be convinced that it's a transparent signature. And then you can put this out on your distribution mechanism again, and it's similar to before. Instead of having the data and the signature, you just put the data and the proof instead. And I want to emphasize here that this is a risk, and it's not for free. So what you're doing here is you're basically saying that, well, you do care about detecting what's happening with signatures that happens with your public key, but you're also going to depend now on the log being available when you want to submit here. So you have to kind of balance those two together before you start doing this, because otherwise you might find yourself not being able to sign. So there is a risk, but the reward is also really high if you do it. So if you want to submit something to the log, there's basically, again, RFC 6962 Merkle tree. And what we're storing in the leaf is a hash of the public key, a double hash of the data, and then there's the signer's signature on this double hash. And the reason why this is a nice thing to store as a log operator is because basically there's just two hashes and the signature, so you know that there's not going to be some funky, copyrighted metadata or illegal content making it into this log, which could be an availability concern because the log is append only. You can't take things down. So this makes it a bit easier to operate this log without being very worried about taking submissions from people that you don't really trust. So in order to get one of these leaves added, you can, as a signer, submit an add leaf request. And what you provide is the public key that you should use for the verification. You provide a hash of the data. So the log doesn't actually see the data, only a hash of it. So it's nice for performance, but also nice because then the log can't mint the data. And then there's the signature on this double hash. So what the log will do, it will compute the double hash. Now it knows it's a checksum, verify the signature, and then create the entry in the log. Then after some more additional HTTP API calls here, you're going to end up with this proof. And the proof is not that magic. It's still the signature that we had before. It's going to be an index in the log, so a leaf index. Then we're going to have like the nodes in order to do the inclusion proof. Then we're going to have this checkpoint again that Al was talking about. So for those not familiar, you can think of this as a signed tree head. So it's like a tree size, and it has a root hash, and it has a signature from the log. But it's also going to have those signatures from the witnesses, which are helping you claim that this is an append-only log and it's globally consistent. And the way that works, very briefly, so I'm not going to go into detail because we have plenty of talks on this later. But basically, the log is going to, when it wants to create the next checkpoint, say to the witness that, hey, here's my next state, and here's a consistency proof. And if the witness can verify it, it's going to say, well, looks good to me, it's append only, and then it's going to provide a co-signature back to the log, and then you can just put that into the checkpoint and start serving that to the users. What this co-signature means is that it's append only, or it's the largest append only log that the witness has seen at this particular time. And having the time here is very helpful for freshness for the monitor, and you can also start actually doing like timestamping of figuring out like when these things actually get logged, which is pretty cool. But yeah, I'm going to defer this to the later talks, so there's going to be plenty more witnessing things, and there's in very small the specs in C2SP if you want to click them later on the slides. So putting all of this together, on the right, we still have the signer, the user, and the distribution mechanism. The only thing that changed is that instead of having the signature, we now have the proof, and instead of having just a public key, we have a trust policy. We have the monitor in the middle, which is able to pull all of the signatures and be convinced that it's getting all of the signatures that this user is going to accept as valid, because it's failing closed on this trust policy. And then we have the witnesses here to solve the split view problems, and the witnesses to solve the freshness. And then, of course, the log, which is just storing those signed checksums. So coming back to this table, Anti-poison is this risk of, well, basically a poison log is the risk of getting some illegal content or copyrighted content into the log. And the way we solve this in Sigsum is to make sure that we don't have any arbitrary bytes in the log. You actually don't need them in order to achieve signature transparency. So we have 2 hashes, a signature, and that's it. For anti-spam, I didn't talk about it now, but we can basically make the user do a one-time DNS setup. And then you can rate limit on the domain name, or you can, of course, also rate limit on public keys if you want to. Sure, you can come up with plenty of other rate limit mechanisms, and those are not integrated in the log spec per se. They're optional parts that you can add on top of it, but that's the ones we have right now. For the API and the formats, we basically have some HTTP APIs and some well, data structures you can write by hand, like the checkpoint, for example. Very simple, very easy. Cryptography, we're quite opinionated, so we only use the SHA-256 and the ED25519. Might stand out at first. Reason why we didn't try to support all of these legacy options is because if we want to have this failed closed story, we ought to be able to update like the user software, for example. And then it doesn't make that much sense to try to support all of the different existing formats out there, because then we're going to be able to log a whole lot of stuff, but not be able to verify a whole lot of stuff. So that's why we went in this very narrow direction. The data structure, it's a chronological Merkle tree. We already covered that. When it comes to SCTs, so this is this promise of logging that you may or may not have heard of from CT. Short answer is we don't have them because we don't need them. Happy to talk more about that, but this goes back to this reactive auditing and the gossip, and yeah, that is just causing a lot of headaches also for the operations of the log, because you might make a mistake and then things disappear, which is not nice. Sharding, so it's this way of basically how do you shut down a log. So in CT you have temporal sharding, so once all the certificates have expired, then you can just safely shut down the log. In Sigsum we have signatures. They don't expire in the same way, so it's not really applicable to do sharding, so we don't have that. The silver lining is that verification for the user is offline, right? So even if we shut down the log and we want to rotate it, nothing actually breaks. So we can kind of do sharding, but we don't actually have it. So you still want to keep the things around for the monitors for some time, but maybe it becomes a tar file at some point in the future. Split use, we're using witness co-signing. Plenty of people are going to talk about it, so I'm not going to cover it. The only thing I'm going to notice is that we have basically a way to make the witness, even though it's listening for requests from the log, you don't have to run this on a public internet endpoint. So we have a way to basically hide the location of the witness, and this is great for reducing the attack surface. So since this is where trust is coming from, we want to make sure that it's as hard as possible to get in there and do bad things. And finally, we have the submitter privacy and the user privacy. So in terms of submissions, you can do, you submit the hash of the data, and that's what you're leaking. And if we have rate limits on this, then of course, if you provide the domain name and you validate the domain name, then you're leaking the domain name. But other than that, I think we've done a pretty good job of not leaking things to the log when you're submitting. And for the user privacy, nothing has changed. So whatever issues or non-issues you had before with your distribution mechanism, that's what you will have after as well. We have a getting started guide on Sigsum, and we're also going to have a birds of a feather session on Sigsum. So we're happy to talk about your use case, what you would like to use Sigsum for. If it's not working for you, then we would like to know why, so we can do it better. So a bunch of extra slides that I will show on the birds of the feather session later. So I'm just gonna jump ahead to the end and say that the takeaway here is, let's remember where we started. So we had this initial setting with a signer and assign some data. You already have a way to distribute this data. And then there's a way to sort of distribute those public keys to the software. So we're not solving data distribution, we're not solving key distribution. We're just helping you discover which digital signatures have been produced by what cryptographic signing keys. And this is what you get with Sigsum. You don't change the flows here for the user, so it's still offline verification, which makes it a lot easier to incorporate. You can still have the monitor now that discover the signatures, and optionally you can make those additional claims about where you're storing the data, what type of data is it, what can you falsify about this data. It's not something that we do per se in Sigsum, but you can do it with Sigsum if you want to. Some next steps. most important, we need to continue growing this witness ecosystem, and now we have basically interoperable specs, which is great. Now we also want to make sure that those specs run on production witnesses with good business continuity, because if we don't have that, then we have basically nothing, and we're back to the drawing board. So that's really important if we want to have a secure system. The other one is we're hoping to get some more independent Sigsum log operations. So this is an availability risk if it's just a single log, but if you have a few different independent logs, it makes it a lot less scary to actually start using this. We have a bit of as all projects, I guess, documentation backlog. We have a good getting started guide for like the key usage transparency, but if you want to start doing things with the claims and the data, it's basically in the heads of the people working in the project right now, so we need to flesh that out. Some hopes for the event. So I would like to talk a bit about how we configure witnesses, for example. So I've been noticing me and Al are sending a lot of emails back and forth lately with log public keys and witness public keys and different endpoints. And if we could find a way of like sharing configuration, I think that would make, well, our lives easier, which is great. And also as this system grows, it's not going to scale that well to send emails. And it can also reflect a little bit about, I mean, if you want to make a second version of Sigsum in some form in the future. So I mean, we are quite happy with a lot of the choices that we did in this table, but that said, there are always things that can be improved, and things have happened the past 4 years. So one example would be like the tiled APIs. If that would have existed 4 years ago, I would have selected that. Another user feedback is that even though ED25519 is great, sometimes you might want an IST curve, and it's not a bad choice. So maybe it should be slightly more permissive, even though we might not want to go all the way to like GPT signatures. Few other, minor things that you could consider changing. But yeah, if that is something someone's interested to discuss, I would be happy to. So with that said, that's my introduction to Sigsum and how you can use it. There's a bunch of links here. You'll find the Getting Started guide on the project site. You'll find some other information about the log that my company Glasklar is running. So we have a production log that you can use for logging. If you want to get an introduction to that, come to the Birds of the Feather session on Friday. All right, that's it. Any questions?
There we go. Question about witness discoverability.
Yep.
So you mentioned that witnesses are contacted by the log itself for
Yep.
countersignatures.
Yep.
How does the log discover the network of witnesses to communicate with?
Al and I send emails to each other.
Nice.
No, so it's literally like a configuration to the log currently and configuration to the witness. So the log has like, here's the public key and here's the URL. And in practice, it's the URL to Bastion host, which is going to help you find the witness. And the witness is going to connect to this Bastion host with some magic that Fillipo provided.
Thank you, Fillipo.
Crimes.
But yeah, so currently we don't have a very good story for sharing that configuration, and maybe we should put it in a transparency log.
Thank you.
Hey, sorry, I was wondering what would be the recommendation in a case when you're having a set of binaries? Is there some idea of how to link them, how to log them? Do you log them separately and then, I don't know, link them in a policy or what?
I think you could do either. The most important part is to be clear about what you're doing so that people can falsify those things. So you can do it either one binary at a time, or you could batch them if you wanted to. Just be very clear about what you're doing so that when you do write the monitor for it, or if someone writes the monitor for it, which is the point of doing the logging, then they know exactly how to interpret it, how to discover the data, how to falsify the claims.
Okay. In terms of the flow, I just like on the end client, you need to do the verification and checking. So how does that been deployed in the system right now? What is the state?
Yeah, so I mean the state of using Sigsum is that most people use the command line tool. So there's like a tool called Sigsum Verify, and that will take as input this trust policy of what is the signer's public keys, what is the log's public keys, what is the witness public keys, how many witnesses do you want in order to consider this secure. And then you would use this as, you would verify a signature, but now you just verify this, as Fillipo would say, spicy signatures. And you can, of course, integrate this into applications, so that, it's just wrappers around Go libraries. But as far as I know, there is no one that is publicly doing that on the line yet. So we just got the log, which is the production log, up and running last week before the event. So maybe we'll have some actual production use cases sometime soonish.
Okay, thank you.
Son? Just a small question. So you mentioned that you hash the data twice.
Yeah.
What is that for?
Yeah, so suppose that the submitter just submits the hash of the data and the signature on that. From the log's perspective, you don't really know if they hashed anything or if they just submitted, 32 random bytes or 32 not so random bytes. You can't distinguish that. So by making the log do one of the hashes, the log can be convinced that it's actually storing a hash and not 32 arbitrary bytes. So this is just to reduce the risk that something illegal or copyrighted makes it into the log.
So the log does one hash,
yeah,
but then potentially the client does another, but we don't know.
Yeah, so the verifier always does the double hash, right? Because that's how you verify the signature. Signature is always on the double hash. But when you're submitting into the log, you hash your data once. Then the log hashes it again, and then the log verifies the signature on the double hash.
Okay, thank you.
Lisa?
Yes, so I mean, if you want to have 32 arbitrary bytes and you want to submit them, then you can do that, and the log will hash them, and the hash is what gets into the log, and then your verifier and monitors and the stuff all needs to know what you're doing, but the Sigsum system doesn't need to know.
Any other questions?
Yeah. How do you bootstrap the system? Because you need to discover the witnesses' public keys.
Yeah.
So how do you bootstrap that?
So our starting point is that you have a way to distribute keys to your users. So you're going to bootstrap in the same way that you distribute keys currently, and instead of just distributing the key, you're going to distribute the log's public keys and the witnesses' public keys as well. So we're not solving key distribution or the bootstrapping here. But if you do solve that problem, you can use this thing.
Another question?
Yeah.
So you need a quorum of witnesses to sign every single Merkle tree root?
Yes.
Okay.
Easy.
There are no other questions, and yeah, let's give another round of applause to Rasmus. Thank you very much. That was excellent. Okay, we are going to stop for a break now. We're going to have a good long break so you can digest the keynote and the Sigsum talk, and we will resume at 11:45. Thanks.
So yeah.
Okay, we'll be resuming in a minute. Quick folks have been asking about the speaker slides. We'll be sharing those for those of you who are on the Transparency.dev Slack. I'll drop them in there once I get them from the speakers, and we'll also make them available on the speaker pages. So if you look at the schedule on the website, we'll be adding them in there as we get them from the speakers. So yeah, please check there. Okay, we'll just give everyone time to get back to your seats. Okay, so we're going to have two main talks and a lightning talk before lunch. And for the next talk, I would like to introduce you to Al Cutter and Martin Hutchinson, who will be talking about Tessera. Please give them a round of applause.
Hello, I'm Al again. This is Martin. Yeah, we would like to tell you about Tessera, which is the next version of Trillian. I'll start by talking a little bit about Trillian, and as is my theme for the day, I'm going to talk about the good old days, the evolution of it. And then I'll sort of quickly talk about some of the things we might have done differently with hindsight, because hindsight is 2020 after all. And then Martin will take over and tell you actually all the interesting stuff that you'd like to hear about for Tessera. So Trillian's been around since 2016, more or less. As I said before, it's application agnostic because we wanted to encourage the growth and existence of other ecosystems. It was built sort of in a microservices fashion because that's what we did then. So you would end up running a bunch of binaries to host a Trillian log. You'd have your personality binary that implemented the protocol, access control, encodings and whatnot for whatever application it was you were building. That would back onto a Trillian log server, which would be sort of chatting away via gRPC and do the business of submitting things to be integrated to the log. There would be another binary for integrating stuff into the log on a schedule, and then you probably run an etcd, you might run Prometheus, and I don't know, a whole bunch of other stuff. And it turns out that was quite a lot of work. So we also made Trillian be multi-tenant aware to try to amortize the cost of having this large set of infrastructure running. Trillian has always been tiles-based. It was always tiles internally because it makes a lot of sense when you're storing stuff to group them up together and batch them when you write them. But we never exposed any of that. It was only really a storage implementation detail, which is quite exciting to sort of see it break out of the confines of Trillian and up to becoming a first-class citizen. We'll talk a minute about Tessera, but Trillian's still actively maintained. We know that it's still being used. CT is still running on top of it and probably will be for at least a little while. We've made changes recently, like Martin made the change to do the revisionless storage at the beginning of the year, which actually has quite a huge implication for cost savings. That if anybody's running shards for 2026 or whatever, hopefully you'll benefit from that. But there aren't likely to be any new features coming or landing because we're all very busy and focused on the next generation of logs, which we'll tell you about in a second. So what did we learn over the last 10 years? I've sort of hinted at a bunch of it now. But if we were to do it again, we would probably make it simpler in terms of using it from like an application development point of view. We would make it operationally a lot less complex. and probably a simpler code base as well, because that obviously makes our life a lot easier maintaining those code bases, and it makes it a lot easier for folks that want to contribute. We'd also make it so that you only pay for what you need. Trillian, was able to scale fairly far in terms of throughput and log size. We would test them up to multiple billions back in 2016. But as I mentioned earlier on, there are other use cases where you actually want to scale down quite a lot. So you don't need to run this big cluster of stuff if you only want to add a thing once a month. So it would be nice to be able to do that too. And then also in terms of complexity, you shouldn't pay for complexity or behaviors that you don't need. So for example, Trillian always has its atomic sort of deduplication mechanism running whenever you submit things. You can subvert that if you don't care about it, but it's always there. And so if you don't need that, you shouldn't have to pay the cost and the storage for it. We also try to make things be a little bit more infrastructure native or idiomatic. Trillian sort of specifies a bunch of storage abstractions that you need to meet, and they were designed with very much a view towards transactional storage infrastructure. But things move on, there are different things now, and having those abstractions set as they were made it a little hard to implement Trillian storage in terms of other types of storage. We'd also probably change the balance between synchronous and asynchronous API calls. If you're aware, when you ask Trillian to add a thing to a log, it says, yeah, sure, I'll come back and I'll do it in a bit, and then at some point it does it. It turns out that it's quite useful to be able to have that happen a little quicker. So, maybe rather than going fully synchronous and having everything integrated and updated, within the call to add a thing, is there a middle point that we could use? And I think the last thing that we would do is try to make it a bit more opinionated. So we tried to make Trillian able to do whatever it was that you wanted to do, as much as was reasonable. But I think over the years we've learned that there are good patterns and approaches to doing things and some that are not so good. And so we would have probably made it a little more easier to do the right thing and a lot harder to do the wrong thing. So I will hand over to Martin now.
Cool. Thanks, Al. I'm just going to make that a bit bigger. Right, so yeah, that's a really good background on how we got to where we are now. So hi everyone, I'm Martin, and I'm going to give you a quick overview of Tessera. So we've spent most of this year kind of experimenting with different technologies and then designing and then finally building Tessera. And so yeah, it's kind of quite a thing to be standing here now and sharing yeah, our next generation of log technology. So we've got a lot to cover, and a lot of this talk is going to be quite high level. So there'll be parts where we don't have the opportunity to go quite as deep as I'd like, and maybe some of you would. But that said, at the end of all of this, you should have a good understanding of what Tessera is and how you can get started with it. I should have actually spent a little second there talking about this slide. So Tessera is a lightweight Go library for building tiled logs, which is mostly understandable, but maybe there's a few people. If there's anyone in the room that doesn't know what tiles are, then you're going to be quite lost, I think. So we'll start with that. As Al says, tiles have been around for ages. So Trillian uses tiles in the storage layer. So it's been around since at least 2016. And Tessera is also using tiles. So it uses them internally, but the big difference is that it exposes them as a first-class API concept. That was pioneered, I think, first in the Go Sum database. And that's now a spec, and so we expect this to be what logs going forward start using as a kind of a standard API. And so given that significance, I think it's important that we've all got a shared mental model of what tiles are. So strap in. The primary purpose of tiles really is about making it so there's efficient lookup of regions of trees. So whether that's for inclusion proofs or consistency proofs or any other kind of inspection. What we're aiming to do is give each part of the tree an address. So think of that like a postcode or a zip code. It allows somebody to easily just look up a region of the tree and get the data that they need. And if that's all you take away from this slide, that that's what tiles are, then that's absolutely great. But some of you have probably spent a bit of time playing with Merkle trees and binary trees and want a bit more of an idea of like how these are constructed. So very quickly, I'm going to go over like how that's laid out. So after this talk, you might want to grab yourself a big sheet of paper and a pencil and draw a binary tree with a couple of thousand leaves on it. And then all your leaves will be at the same level if you've constructed it properly. So that's great. Start there, move about 8 nodes up, get a ruler and draw a line all the way across. And what you'll be left with is a slightly less big binary tree at the top of that line and a sequence of binary trees below that line. And if you keep repeating that as you go up the binary tree, then you'll eventually run out of space and your job is done. So you've now got a coordinate system. So this is our postcodes, right? You can pick a level of the tree. So starting in the bottom left corner, 0, 0. And then we can go up and pick a level, and then we can go across and pick which tile it is that we're looking for. So there's a URL there that shows that we're looking for tile 2, 1. So we start at the bottom left, we go up 2, we go across 1, and that's the tile we're looking for. And as I said, this is all now a spec. And if you want more details on this, then the spec link is there. So that's tiles. Now, hopefully this description makes sense to everybody to a degree, but we're still going to go into details over what it is, right? So we'll start with lightweight. We'll go in order this time. So Trillian's more lightweight, as Al's already talked about this a fair bit, actually, because we've taken this approach of not having a single flexible code base that can adapt to different environments and different storage implementations. But we now have sort of 4 native idiomatic lightweight implementations. 2 of them are cloud native, so we have GCP and we'll soon have an AWS implementation. And we've got cloud agnostic implementation, so we've got MySQL and POSIX file system variety. So while these are sort of 4 different implementations, they share a lot of code around queuing and things like this. And from a user's point of view, which probably concerns most of you, all 4 flavors basically behave the same. And programmatically, you use them in very, very similar, the same way. It uses duck typing, so you could swap one in if you started with one and you want to switch over to another. Reads are super cheap, and we'll talk about this a little bit later, but basically this is because of tiles. It makes scaling the read traffic, which usually turned out to be a problem with scaling Trillian. Read traffic is now super cheap, and basically the moral of the story is we try and make somebody else do it for you. And so, yeah, gone are the days of profiling MySQL queries to optimize the read path. And it's also a lot simpler. So Al's already talked about this, about multi-tenancy. But it used to be the case that you'd have one storage location, and in that storage location, you'd stick multiple logs. There's no need to do that anymore. And that means that when you've got to this point where you've brought up 3, 4, 5 logs and you need to delete one of them, there's no longer this sort of quite a dangerous feeling situation where you want to delete one log and keep the other ones running. Like, understandably, that's quite anxiety ridden, and your playbooks need to be quite detailed to make sure you're not doing a dangerous thing there. So that's gone. Each storage location has a single log in it, so hopefully a lot simpler to operate. So it's lightweight. It's also a library, which is in stark contrast with, as Els talked about again, with Trillian, which we distributed that with these microservices, which we thought we were doing everybody a favor by giving them microservices. Like, hey, you just call that thing, you can write your code however you want, and you call these microservices. And programmatically, I think that is still true, but where it lets itself down a little bit is around the deployment time, which is actually where, you're spending a lot of your time once you've written the code, you're deploying it, and you're maintaining that for years. And if you're not doing it in a way where your idea of what microservices are matches with the way that we package those microservices, then you're going to have a bad time and you're going to have a lot of friction. So we've taken a completely different approach here, which is Tessera is just a library, which means you get to deploy it however you want. So if you want a monolith, you can do a monolith. And if you want microservices, you can go and have all the microservices you want. It also makes it a lot easier to kind of, you can still use a physical machine or VMs and Kubernetes and stuff, but you can also easily now bind this into like native, scalable, elastic kind of front-end technologies, so like Cloud Run, for example. And speaking of scale, you can go from a single instance, but we also support, which we put quite a bit of time into the design of this, into making it so it can work regionally or globally. And that's a really important thing. I think Rasmus talked about this earlier, about how uptime on the logs can be super important. And one way of doing that, of course, is to have multiple logs, but another way is to make sure that your log has more availability. And so having it in multiple regions and globally is one way of doing that. And finally, yeah, there's a little bit about instrumentation. I feel like I'm a QVC salesman or something here going on about this, but But you can do it your way. That's basically the moral of this slide. But whatever build chain you want to use, whatever monitoring libraries, debugging libraries, whatever flag system libraries you want to use, we don't have opinions on that. You can have your own opinions, and we won't get in the way. But where we do have opinions is around the sort of the API that you're expecting to be serving your read API from. So it's tiles. You've probably got that idea in your head by now. And so the big difference is that we're storing the tiles serialized according to the API format, which basically means that at read time, so storage is the read API, and so reading these tiles from the storage and sending them through the API requires basically zero or minimal transformation, which means it scales well and costs you very little. These are the two tiles formats we support. So the tlog tiles API is the one that we expect most new logs to start adopting this and using this one. There's also obviously those in the CT world will be familiar with the CT static API, which is similar but a little bit different, and we support both of those formats. So who can use Tessera? Anyone, but as long as you're using these two log formats, or one of these two log formats, you're not going to use both. And unlike Trillian's been around now for 8+ years, and so there's a lot of people who have gone through the onboarding process. Tessera's new, and so you're going to have to be prepared to be an early adopter. I don't think that's too scary because we're all friendly here, but it is just something to sort of bear in mind as you get started. So I think that's enough about the overview of everything. Now we're going to just go into a few little details, right? So this is an example code snippet. I said it was lightweight, and I think this hopefully shows it, right? This is about the extent of the API that you're going to see as a client. The first thing you're going to do, whichever storage choice you've made, is you're going to need to instantiate a storage. In this case, this is obviously using MySQL. And so we call it MySQL new. We pass it a database connection, probably for obvious reasons, and then we need to pass it the signing material that it's going to use for signing checkpoints. That's a var-args construct in Go, so we can pass in other optional parameters there that control things like batch sizes and pushback. So there'll be other little bits supported, but those are kind of as you need them. And then you've got your storage object. Great, and then the next part of it is going to be adding stuff to the log, and funnily enough you do that through calling add, and then you call the add method, and as written there, that code will take your new leaf, add it into the log, and give you back, it stores it temporarily, it sequences it and gives you back an index, and that is the index that's durably assigned, and you're safe. You can return that to clients or use it as you wish. A short while later, asynchronously, it is going to be integrated into the log and made available through the read API. At the moment, you'll have to wait for that, but by the time we hit alpha, one of the big things we're going to have is a utility for those of you that do need to block until it's made available through the read API. We'll have the utilities there so you can block. But for most people, we think just doing it this way is going to be what you need. Right, the next slide's going to go really quite quickly because it's a demo and we don't have a lot of time. So the purpose of this demo really is to show you how quickly and easy it is to get set up running it. And to just get started with playing around with Tessera. So here I'm doing Docker Compose to bring up the MySQL instance. I told you it goes fast. Grab some environment variables so we can make some curl requests off the command line, and then we're going to put a few things in the log. So that 1, 2, and I think 3 is coming up. And then they're sequenced and integrated now, and then we're going to just show a few quick GET requests to prove that the data is in the log. So that's the checkpoint and the tiles, the tile with them in, and then we're going to quickly have a look through with the inspection tool. So that's probably quite stressful, and it wasn't meant to be, but it's just supposed to show you that it is just a handful of commands, right? I did consider dropping that, but then otherwise I'm just showing you this slide that's like, and we've got some examples, right? So that GIF that has what I just showed you there is there, so you can watch it in slow motion or as many times as you want, but the script is also there, so you can you can go through it and follow it yourself, and it is just as easy as Docker Compose and a few curl commands to get started. So that's the command conformance MySQL that I've just demonstrated there, there's also a very equivalent one for GCP and POSIX, so you can get started with those as well and just have a little play with them and see how easy they are to deploy and to just interact with the log. And then there's a few other examples. So all these examples here are written in a way where they have a day job, which is so the conformance is to make sure that our performance and correctness is as we expect, but they also serve like a side gig, and that is making it accessible so that people can understand, come and look at the code that's there. It's intended to be accessible, so you can have a look at it and see what usage of the Tessera's APIs look like. And so I did sort of promise this, and so this is the last slide from me. A quick overview of the 4 different implementations that we've got. Well, I'll go over 3 of them. So GCP uses Spanner. So when you call that add method, they go into the new leaf goes into a Spanner table, and that's where it's durably assigned while it's been sequenced. And then when it's integrated into the tree, it will be moved from there and compiled into a tile that is stored in GCS. So the Spanner table is only used for stuff that's not integrated yet, which means it stays small, and that means your bills can stay small too. And then Google Cloud Storage scales and cost-wise as well, really quite nicely. And then you're just getting Google Cloud's GCS to serve your reading for you. And I think they've got quite good at serving read traffic now. So yeah, AWS, we're going to skip that one right now. But MySQL, obviously this one's a little bit different because you do need to serve a read path. You can't just hook your database up to the internet and expect that to go well. So each of the tiles is stored in a row in the database, and it's a point lookup to get a tile, and the way that it's stored in the row is basically as it's needed for the API. So it's while you do have to serve the read path, it's just a point lookup and very little kind of cycles needed. And then POSIX is just a file system, right? So the log's constructed there. And then if you need to serve it through an HTTP server, like we've had HTTP file servers for quite a while now, we're quite good at that. So that's the way you'll serve that one. So back to Al, throw him under the bus to tell you about the status and the timeline.
Can we have it yet? Basically, yes. It is ready for you to play with it, so please do go and play with it. We're pretty confident in the 3 storage implementations that are there. The AWS one, as Marta mentioned, is coming real soon now, but don't wait for that. Just jump in and start swimming. Performance, it heavily depends on where you're running it. So, we're shooting basically for a minimum bar of 1,000 writes a second on sort of the cheapest configuration that you can have, which should be more than enough for now. It will scale higher if you are willing to pay more. So, for example, with the GCS, GCP storage, as Martin said, we use Spanner. That 1,000 writes will come if you use the smallest possible, cheapest Spanner bill. They recently sort of allowed you to use fractional servers, and so you'll get 1,000 QPS out of 100 Spanner performance units, or whatever it is that they call.
That's writes.
Writes, yes. Reads are obviously just from buckets, and so scale as big as your wallet is. Next steps, as I already said, really for you folks to pick it up and start playing with it, because we really want to know if it works for you, and we really, really want to know if it doesn't work for you. Is it easy to use? Is it tricky to use? What could be better? What's missing? Do you have one of these weird sort of corner cases that can't be satisfied with the API surface and sort of envelope that we have? If so, definitely want to hear from you. And yeah, as Martin said, we have the conformance and example binaries, which will serve as nice, simple entry points for you. It's super easy to run them. They mostly just work with Go Run, Docker Compose, or Terraform if you're into that sort of thing. That is all. Any questions?
Thank you. This is great. For certificate transparency, it's going for immediate sequencing, trading high availability for having immediate sequence numbers. That's the good trade-off. You say that you also have the global one where you have multiple writers. How is the performance? How do you do that with the immediate sequencing, and how is performance impacted?
That's a good question. So the way we do it is so I mentioned earlier that we wanted to be more idiomatic about our storage implementations, and so the way we do it is, however it would make most sense to do it on that storage implementation, which I know is a rubbish answer. But for example, in the spanner one, we have that spanner table that is about cluster coordination, and so we do sequencing by simply having a row that is, what's the next sequence number that's available, and then another row which takes blobs of pools worth of stuff to be sequenced, and so we can sort of sequence multiple entries at the same time and chunk it in there.
So it could well be it's a spanner-only feature.
Well, so that's how Spanner works.
Yeah.
AWS will do something similar-ish. MySQL's got transactions, so you do it there. The sort of global availability might be sort of slightly weaker there. POSIX uses atomic POSIX operations, and then like advisory locking just to sort of stop the fighting. But it would work even if that failed, with a lot of fighting. But then, you'd probably be looking at running on something like Ceph. So I did try it with Ceph, a cluster of sort of 3 nodes, and it was fine.
Thanks. Oh boy, I have so many questions.
Fortunately, we're here for 3 days.
Yeah,
so.
Yay. I'll start with one. Is it better in every way, or are there any downsides compared to Trillian? Obviously, Trillian is more mature, but when it comes to the design, is it strictly dominating Trillian, or yeah?
I think maturity is an important aspect, but other than that, and as far as I'm aware, it's better in every respect because it's much easier for you to pick up and use. It's cheaper for you to use. It's cheaper for you to run. It's easier for us to maintain because it's a lot simpler. It doesn't push you down the route of having SCTs. And unless there's something that one of you folks or some other folks somewhere really wants it to do that it doesn't do, that you can do with Trillian, then please, if you're looking to stand up a new service with logs, then use Tessera.
Thank you. So the one thing that I would say is that obviously it only works for people that are using the the tiled APIs that I talked about. So if you've got a legacy reason or your own novel reason for not using those APIs, then that's the case where you say you're going to have to stick with Trillian v1 as it was. But really, come on, join the party and move onto tiles.
Yeah, I think I'd class that as a plus point, forcing you to sort of catch up with the rest of us. But I mean, also actually, if you really needed to maintain compatibility with the old stuff, you could run a read proxy, right? That just sort of pulls nodes out of the trees to rebuild old style proofs or whatever, if you really wanted to. But
thanks for the talk. If a new organization comes up and want to set up a new CT log, what would you recommend to use to her?
Well, I mean, so obviously we're at an interesting point at the moment with CT, with the sort of the Sunlight experiment, CT static API. I mean, I don't really have an answer for you. I mean, you could run both. That might be a great thing to do if you were looking to get into the CT ecosystem. We don't have a lot of 6962 logs, so having more would be great. On the other hand, you've got the qualification period in order to become a trusted part of that ecosystem anyway. Yeah.
More about these legacy APIs. I would be happy to use Tessera as those backend storage for Sigsum logs where we currently use the Trillian daemons. But I still want to support the API where you can ask for inclusion proofs and stuff. Does Tessera do that for you, or would I have to write my own code to produce an inclusion proof, or how would that setting work?
Yep. So there's not really support at the moment in Tessera for doing that, but you could totally do it because ultimately all you're going to do is go and fetch the nodes and then bundle them up in whatever format your protocol wants. So we do have, I think, a client for integrating with tile-based logs, and so you would use that in your personality to go and construct the proof and then return it.
Sorry, can I just get Hayden to come set up, and we'll keep going with the questions.
In regular Trillian, you have some different modes for the log, like pre-order log, for example. Have you removed this now, or is that still there?
It's not there at the moment, but it is intended to be there. We know broadly how we will hook it in for the various storage implementations. It's just we want to have people using this as soon as possible so we get the feedback so we can make whatever changes are necessary. So we decided to sort of invite you all now, but yeah, it will come. If this is something that is really important to you, like, come and talk to us.
Yeah, that would be fantastic. So we're actually using that for replicating the Sigsum log server between the secondary and the primary, and then we can do that without having to deal with MySQL database cluster things.
Yeah, for sure. Yeah, it will be there. I mean, there are other really interesting use cases for logs where it's important that you put a thing at a particular index as well, so I want it to be there too. You afterwards.
Plop, plop, plop. Okay. So as I understand, like Tessera, the other way around, is meant to like facilitate and reduce operational issues. If, as you're inviting people would like to try it out, which metric would you like people to look for to understand if it's operating properly?
I mean, pain is probably the most important one. Reducing it. Well, I mean, it depends on the day. With Monday, it's not so good. But try it. Correctness. If there are tools that we have, like the witnessing code base and that sort of stuff that you could run locally to basically check that the log is doing the right thing. There are a lot of checks internally to make sure it does the right thing. I'm not so worried about that. Obviously, I would really love to know if it does catch fire and burn your house down. Please tell me. But what I really, really want to know is, does it solve your problems easily and smoothly and makes your life happy? Ben has been asking for ages.
Oh, sorry. We'll keep going with the questions.
Talking of pain, MySQL.
There's one for you.
So I have a question around, would you recommend large logs use MySQL? I assume the tile blobs are stored as blobs in my MySQL table, and for me, sort of as a system administrator style, that seems kind of like hell. I'm curious on what is that a long-term recommended path, or could we see a solution where it's more like the GCS system, while you sequence in the MySQL table and then you dump it to a file system or S3, Ceph, whatever, like S3 compatible API?
Yeah, exactly. I mean, these basically we were very opinionated. We were going to have these sort of cloud native ones that use bucket technology on the front end, and we already had the serverless log which use file systems, and so we did that. But there seems to be this sort of gap in the middle, and so that's sort of the MySQL one is sort of to patch that, and then we'll sort of see how it scales. Hopefully, because we can support MySQL, we can support other relational databases as well. But the point is obviously there that they're not really a good fit for sticking huge blobs of data in. But it is a good way of a bunch of people getting started, and for certain small to medium sized logs to operate. And yeah, the Tails API, you should be able to just stream these out and put them somewhere else. So there'll definitely be ways of doing that. That might be stuff that we welcome contributions from the community. Or if you're just sit there lazily kind of demanding it and banging your feet, then maybe we'll do it ourselves. But contributions really are welcome.
Okay, thanks.
Just to add to that, the reason, so we were opinionated about sort of the various domains that we wanted to have implementations for. The reasons we landed on these particular ones is because we went out and spoke to a bunch of log operators and said, what is it you run? What do you want to run? And with the magic wand, what can we give you? And some asked for MySQL.
Hey, do you have some numbers comparing storage capacity costs of Tessera and legacy Trillian? Can I say legacy?
You can say legacy. You can
legacy
say
Trillian.
Vintage Trillian. Yes, but no. So it's not expensive. So the easiest way to actually have that answer is to go onto the cloud or the AWS, calculator thing where you say what it is you want, and then it tells you how much you're going to pay. Because you know how much stuff is in your log, and I don't really know that. But the GCS one, for example, when you choose Spanner, don't say I want a span server because that's really expensive. Just say I want PUs, and then the 100 is the smallest it will let you do. And then you choose whether you want replicated Spanner or you're happy with sort of regional replication. GCS, similarly, you can have like, multi-region or, whatever, and it all gets more expensive as you go. You know what it is that you want to do with the log most.
Okay, but let's say we like to suffer pain and we use MySQL, right? And we have same size tree in Tessera and in Trillian.
Well, I mean, the MySQL implementation in Tessera, as Martin said, is the schema is much, much simpler. And it's much less costly to grow it and to serve it. And so I would expect that you would have a happier time growing to that size with Tessera on MySQL than you would have had with vintage Trillian. But I mean, also, try it and then tell us, because if it sucks, then we'll make it not suck.
Yeah, I think we're going to hold the questions there. Al and Martin are around all week, so do pick up the conversations with them, and we have lots of space for discussion. But I'll ask you to give them a round of applause. Okay, and on to our next speaker. I've had the pleasure of seeing the Sigstore community evolve and adapt. So yeah, really looking forward to Hayden speaking about Sigstore. Please welcome Hayden.
Thanks, Tracy. Well, hello, everyone. Today we're going to be talking about the Sigstore project and how we leverage transparency logs for supply chain security and for key usage transparency. A quick bit about myself. I'm Hayden Blauzvern. I'm a software engineer and manager at Google. I'm on the open source security team, or GHOST, where our focus is on making open source software more secure. I specifically work in supply chain security and even more precisely in code signing. All right, so what's the agenda for today? We'll start with a brief overview of what supply chain security is. We'll talk about Sigstore. We'll zoom into Recore, which is Sigstore's transparency log. And then we'll talk a bit about some real-world learnings from our deployment of Recore over the last few years, and then what's next for the project. So, what is supply chain security? Well, to start, let's first describe the software development life cycle, because supply chain security is concerned with securing each of these phases of software development and the transitions between them as well. Software is going to start as source. It'll ultimately be built, packaged, distributed, and then consumed by users. This diagram comes from the Salsa project. If you're not familiar with it, it's a framework for defining levels, where as you adopt more levels, you increasingly get more security guarantees. And this demonstrates that there are many different threats that can occur throughout the software development lifecycle. Just to call out a few, you could have compromise of a source repository. You could have a more sophisticated attack that compromises a build process, or you could have a package registry that either acts maliciously and serves malicious artifacts, or itself gets compromised. This chart comes from some research focused on measuring supply chain attacks, and the main takeaway here is that these attacks are on the rise. You might have heard of some of these before. We won't go through them, but I'll call out a few of the major incidents that happened over the last few years that have motivated a lot of the work in this field. We had the SolarWinds incident, where there was a compromise of source and binaries got distributed to a number of organizations and governments. Log4Shell, which was a remote code execution, not added maliciously. It was a bug in a code base, but the interesting thing there is it was a dependency in a lot of libraries, very, very low down the dependency graph. So people didn't know that they had this vulnerability. And most recently, there was the XZ incident, where there was a maintainer who went rogue, though it seems like it was more someone who was able to gain the trust of the community, become a trusted maintainer, then ultimately end up compromising a build and adding a backdoor into a utility. So how do we start mitigating these attacks? And ultimately, what this means is we need to have trusted artifacts. We need to be able to have a bunch of supply chain metadata that lets us know how an artifact was built, for example, with build provenance, what its dependencies are with the SBOMs, knowing if my artifact is free from reported vulnerabilities with vulnerability scans. Artifacts themselves need integrity and authenticity. And the solution, of course, is signatures. This is obviously the end of the talk. We've solved this problem before. We've generated signatures for many, many, many years, right? Well, I think a key point here is that as enterprises, as organizations, as security-conscious people, we know how to generate signatures. But this is not true for open source developers who very frequently don't know about security or simply just don't care about security. And so what I want to talk about for the next couple slides is some of the problems that we've seen within trying to convince developers and organizations the importance of generating signatures. The first one of these problems is the problem of key management. And there's roughly 3 areas that we like to talk about. The first is distribution. This is roughly the identity problem. How do you know who's the right key to verify some given artifact? Within PGP, this is solved with something like Web of Trust. Next is the storage problem. How do I securely store my key? Do I put it on a flash drive? How do I secure that flash drive? I hope I remember my password for that flash drive that I entered a year ago. What about if I need to have other people signing these artifacts as well? Now I have a key in a shared environment. I'm going to need access control as well. Inevitably, the key gets compromised. Maybe the private key material leaks online because you accidentally included a private key in a source repository. This happens very commonly. Maybe you've simply lost track of your key. So it's not directly a compromise, but you no longer can use your key. Now you need to revoke this key, and ultimately you're back now to this problem of distribution. How do you tell people, I need to go update my key? So this is one of the many problems that we have found with signing within open source. Another one of them is user experience. If you've used PGP before, again, we're a room full of security-minded individuals. We can probably learn how to use these tools, but many developers just don't know how to use them. It's not an easy experience. Another challenge is the distribution of signatures alongside artifacts. And for that, we look to package registries to be able to do this. Maven Central is a great example of a registry that's had support for signatures for many, many years with PGP signatures. PyPI is another example of such, though PyPI is a really great example because there was some recent research that was done that showed that most artifacts in PyPI aren't signed, and those that are, many of the signatures aren't actually verifiable. For example, some of the keys weren't uploaded to Webs of Trust. And again, I'll stress this last point, right, that in many cases, developers don't care about generating signatures. And I think an important point here is they shouldn't have to care. That's kind of the North Star, I think, for many security projects. It's that we can do this silently, that we can add security into a system without users ever having to think about this process. And where does that bring us? Well, this brings us to Sigstore. So we'll spend a little bit of time diving into Sigstore, and then we'll dive a bit more into the transparency part of it. So Sigstore is a convergence of a lot of different standards. You might see many of these and go, well, these have existed for many years. Yeah, and that's what has led us to make Sigstore a very mature product very quickly, because we're built on top of many mature standards. To dive into a few of these, OpenID Connect is one example where we leverage identities instead of keys. And we'll talk a bit more about this process, but roughly, one of the goals of Sigstore was removing the need to manage keys. So instead of managing keys, you're going to manage an identity, one which you likely already have. Or you can also leverage identities that come from workload identities, like service accounts. How do we associate these identities with keys? Well, we do that with public key infrastructure. We issue certificates that bind these identities to keys. We leverage projects like the Update framework to handle the distribution of trusted key material. So we have certificate authorities, we have transparency logs. In order to distribute the roots of trust, we're using this framework, which is responsible for secure software updates. And of course, we'll talk a lot more about how we're leveraging transparency logs as well. I think an important note here too is that this architecture is modular. You don't have to adopt everything to be able to sign with Sigstore. If you choose to manage keys yourself, you're an enterprise or you're a user who is able to manage keys and distribute them, you don't need the identity portion. You don't need OpenID Connect or public key infrastructure, but you can still leverage the transparency logs to have key usage transparency. Just looking at how Sigstore fits into the software development lifecycle, I mentioned that Sigstore can be used to sign software supply chain metadata. So it sits at this bottom layer here, the trust foundation, used to sign software attestations. Ultimately, that's going to get aggregated and become a part of policy decisions about whether or not to trust an artifact. So this is a comprehensive overview of the Sigstore project. I'll have some diagrams in a second where we'll dive a bit more into the technical details. But to mention a few names here, our transparency log is called Recore. We have a code signing CA we call Falsio. Now we have a number of SDKs and clients. The most common client is Cosign. And then we have SDKs in a number of languages. We have some folks in the room as well who help maintain some of these. On the infrastructure side, we operate what we call the public good instance of Sigstore. We have a free-to-use, publicly available certificate authority, Falsio, and our transparency log Recore, which anybody can use. One thing that's very unique about this is we have a multi-vendor on-call rotation that's responsible for keeping these services up. We have a 24/7 on-call rotation. We actually declared that these were productionized and available for general usage back in October 2022. If you want to deploy your own instance of Sigstore, we've published the Helm charts and the Terraform configuration that we use to deploy the public instance. All of this, by the way, is open source, the transparency log, the CA, and all of the clients as well. On the community side of things, one thing to mention is that the Sigstore project is a project under the OpenSSF. If you're not familiar with this organization, this is a foundation under the Linux Foundation. So we have a very diverse community of contributions from a number of organizations and academic groups as well. All right, let's dive into the technical details. So starting on the left side of this diagram, you're an artifact owner. You want to start signing. The easiest way to jump right in is using the Cosign clients. The Cosign clients is the glue. It's going to be responsible for, one, doing the OpenID Connect dance to generate an identity token, and then also generating an ephemeral key. So it's going to generate a signing key that's going to only be used once and then thrown away. At this point, you'll take the identity token and the public key. Cosign will send it to our certificate authority, which will then verify the identity token and then issue a code signing certificate binding that identity and that ephemeral public key. The certificate authority also has a certificate transparency log that it writes to so that you can audit issuance of these certificates to know that if the certificate authority goes rogue or if your identity was compromised and used to get one of these identity certificates. At this point, you now have a ephemeral key and a certificate. You'll use that ephemeral key to sign an artifact and then throw that key away. Now, I'll mention one part of the flexibility of Sigstore is that you don't have to do this top portion if you already manage your own keys. You can also use your key at this point and sign an artifact. Once you've signed it, you're now going to send your artifact, your signature, and the certificate, or a key, but for most of these diagrams, I'll mostly just talk about certificates. You'll send the signed artifact and the certificate to Recore, our key usage transparency log, or our identity usage transparency log. And then you'll get back the cryptographic inclusion proof. For both the Recore log and the certificate transparency log, you can have witnesses that are monitoring these logs for split view attacks and also identity monitors. We have a utility called Recore Monitor, which can monitor the logs for identities. Now, back on the artifact owner side of things, you now have your signed artifact, you have your certificate, you have your proof. You can now go and distribute it. If you have a registry that supports including these, you can do so. And that takes us briefly to touch on Sigstore adoption. Our focus, again, has been on making signing simpler for open source developers. And package registries are very key for open source developers and open source ecosystems. So a lot of our focus has been on driving adoption of Sigstore and signed supply chain metadata within these ecosystems. And we've partnered with the communities and a lot of organizations who help run these various package registries over the last few years. Just to touch on a few of these, NPM and GitHub Actions have added support for Sigstore signed Salsa build provenance. Maven Central recently announced support for adding Sigstore signatures alongside PGP signatures. I won't spoil anything about PyPI yet. Come to the talk tomorrow to hear a bit more about that adoption. And we're actively working with a few other communities as well. Ruby Gems has now started looking into signing and verification. Homebrew is actually leveraging the GitHub Actions support for its support for Sigstore signed Salsa provenance. And then just recently, there was an RFC published for the Basel Central Registry as well. All right, so for the rest of this presentation, we will dive into our transparency log, into Recore. So again, this is the part that we're talking about, which is the record of a signature event. So on the request side of things, when you want to upload an artifact to Recore, you're going to send the artifact hash, a signature, and a verifier. There's a lot of flexibility here around verifiers. Again, for most of this, I'll talk about certificates. You can also use a public key. You can use a PGP key as well. You could use an SSH public key. There's actually a number of other verifiers as well I didn't mention. This abstraction is roughly what we call a Recore type. So this one is specifically the hashed Recore D type. We have a lot of different types that we support. So one of the motivations with this was, as a client, I might not want to implement the logic to extract the artifact hash and the signature and the certificate or key. So a great example is the Java ecosystem. Jars bundle all of this together. So you as a client could choose to extract all of this yourself, or you could also upload a jar to Recore, and server-side, it will extract all of this out for you. And there's a number of other packages that are also supported by Recore. On the response side of things, we will send back an inclusion proof and a checkpoint, along with a signed entry timestamp. And this is one of these places where, when Recore was created, we took a lot of inspiration from CT. So you might see this looks a lot like an SCT. It's signed over the log index, log ID, the body, and a timestamp. And I want to mention two of those. One thing that's unique is we are signed over the log index, meaning we've already included the entry in the log by the time we return a response. And the timestamp is the other interesting bit. So the certificates that are issued are short-lived. And if you want to verify a short-lived certificate, you also need a timestamp to be able to verify proof of possession of a private key at a given point. So you can use these signed entry timestamps to be able to verify these short-lived certificates. You can also use a timestamp from a timestamp authority that implements RFC 3161, which is a bit more commonly in code signing. So diving a bit more into the architecture of Recore. We use Trillian as our log backends. So when we go to upload an entry, we're going to send it to the Trillian log server, which will send the unsequenced entry to a database. The Trillian log signer will periodically pick up those unsequenced entries and then sequence them. Recore itself is going to poll until this entry has been sequenced. Roughly, this is on the order of milliseconds. So clients have an expectation of entries being returned very quickly. Recore also has a search index. So if you have a partial entry, for example, just an email or a subject of an attestation, you're able to look up in this search index the entry. Now, one thing to note here is that the search index is not verifiable, whereas the log is verifiable. It's returning proofs. And this is one thing we'll talk a little bit about in a minute, but this is one of the learnings that we had from Recore, that it somewhat muddies the message when we talk about what is the purpose of the log if you have both data that is verifiable and unverifiable. So getting straight into the real world learnings here. And just to kind of contextualize this. So we've been running Recore at scale for about 2 years now. It's been implemented, I guess it was end of 2020, I think, is when it was first discussed, and then a lot of implementation happened in 2021. We'll focus on API design and deployment learnings from this. All of these, of course, come from our work within Recore, but I do think they're generally applicable to any adoption of transparency for an ecosystem. So these are things to think about either as someone who is designing a schema for a log integration, or as you're adopting logs or deploying them as well. So let's first talk about API design. So I mentioned this earlier. There's a balance of implementation client-side versus server-side. So again, if you have complex structures that hold signatures and artifacts, do you as a client want to re-implement this across a number of different languages, which also becomes complex because, again, to call out jars, most libraries are just written in Java. So if I want to write a client in Python or in Go, now I'm going to need to also handle this logic. What this has led to is a more complex API. And so when it comes to, for example, fuzzing the API, it just means that there's a lot more surface. We've also learned a lot over time around what are the core use cases for Recore. Most of the clients have implemented support just for two types, these hashed Recore types, and also attestations. And that seems to have been good enough for most ecosystems, that most ecosystems were fine doing this client-side parsing and not necessarily needing the server-side canonicalization. So I mentioned this very briefly, but the Recore log right now serves a couple purposes. One, of course, is that it provides discoverability of claims, right? And it returns proofs committing to this. We also are effectively a timestamp authority. We also are a search index. And I didn't mention this. We also can store attestations, though we have since removed some of this capability. More accurately, it's supported for certain types, but not newer attestation types. The first one of these is cryptographically provable. The last three of these require some trust in the log. And so when you're describing the purpose of a transparency log, especially to someone who isn't familiar with this space, it somewhat muddies the message when we say, well, this part is verifiable. These other parts, while they're cryptographically signed, you're ultimately still trusting the log to tell you what is the right index given this search result, right? What is the right provenance given this query for an attestation? So one of the learnings here is it's very important to separate out what is the core duty of the log from some of these other systems. This also helps on the log deployment side as well. So for those of us in the room who are very familiar with transparency logs, this point might sound obvious, but for those writing clients for the first time, it's not, which is if you provide a way to query a system online, many users will simply rely on that. So what we saw from early adoption of Sigstore was many were not saving the proofs that came back from the log, meaning that verification did not become an offline process. It was an online process where you needed to have the log online, which has privacy implications, which has implications for log deployers needing high availability for their logs. The solution from this sounds simple, just save the proof, but there is a little bit more complexity in the data structures. Ideally, we have a way to bind signatures and proofs and verifiers together in a standard specification. And also, of course, we still need the distribution of this. That's another reason why we saw a lot of clients not deal with the storage of these, that they simply relied on Recore as a storage of a signing event. And the last thing to touch on is the need for redaction. If you're signing just with keys, this is not immediately a problem because you're uploading keys to a log, which are just keys, right? There's no risk of additional content. Because of the flexibility of certificates of X509, there's a risk of additional content winding up in the log. And this is an area we've been thinking a lot about, how to balance the need to still be able to monitor the system. You can't just hash a certificate because somebody's going to be looking for specific claims within a certificate, but still being able to redact this content and make it such that we don't have unexpected content that winds up in the log. So let's touch a little bit on some of the deployment learnings now. So we've heard a lot about the cost, and particularly around some of the benefits of systems like Tessera that are going to drive down cost. And there's a lot of dimensions here to cost, right? There's the storage cost of simply storing the data. There's the deployment cost, a lot of services. There's also network egress as well as something to account for. There's another cost that's worth considering here, which is running a productionized service. There is the cost of SREs to keep the service online as well. And this is one of the things that makes us really excited about tile-based logs, about the Tessera project, that the goal is drive down cost and make it much simpler to maintain. I think this is one of the things as well with the Sunlight project that talked about the goal is you need one individual, sometimes not even one individual, less than one individual, to be able to maintain these logs. Another point as well, again, is around having many components to be able to operate this system. You have the front end for the log. With our current deployment, we have Trillian, the log server, the log signer. We have a database. We have attestation storage. We have the search index. As a private deployer, you don't necessarily want to bring all of these components in. So making this more modular, easier to operate is one of our key learnings here. One of the early decisions made with Recore was to not deal with batch processing and to make it an expectation for clients that there would be an immediate response. And one of the learnings here was under high amounts of traffic, this becomes an issue because you aren't able to back off and batch entries. One of the other side effects of this is around witnessing. Because we are very quickly adding in entries, and entries are frequently coming into Recore, our checkpoints are updating so frequently such that there's a very, very low probability that two independent witnesses are able to see the same checkpoint, which means if you want to have a quorum of witnesses, it's very hard to do. And another point here is around sharding. So within certificate transparency, roughly the way that new logs are spun up is every year a new log is created and that log is distributed on a log list. Because we saw a lot of clients making online queries early on, we chose to abstract away shards, creating effectively two indices. You have a global index, which is an index over all of the shards, and an index per shard. One of the learnings here is that as a client, this is a bit confusing. You don't know which index you should be working with, which index is necessary for verifying the inclusion proof versus doing lookups in the log. One of the other key takeaways is that online queries really only need to be for witnesses verifying consistency proofs and verifiers verifying the claims within a log. Done right, we should have strong offline proofs such that nobody needs to be looking up in the log. So you don't need to have this global index, this abstraction layer over all your different shards. All right, so that's been a lot of the things that we've learned from having this deployment. The rest of this we'll talk about where we go from here. And a lot of this is going to be a part of a V2 iteration for Recore. So the first is we want to move towards tile-based logging. And for this, we're starting to already experiment with Trillian Tessera. Again, the goal is driving down cost, making this simpler to maintain. This is very, very exciting. As I mentioned, we are a community-run project. This is under the OpenSSF. And so making our lives easier as on-call, as SREs for this community-run service will be great. And we also are very excited that for those who have private deployments, to also gain these benefits as well. Stronger offline proofs. We want to be bringing together proofs and checkpoints and very key witness co-signatures. Once we have this quorum of co-signatures stapled together, we get offline proofs that demonstrate not only inclusion within a log, but also independent verification of the consistency of the log as well. And again, building this in from the start is going to make it a lot easier, as we won't need to later go back to different ecosystems and go, well, now you need to strengthen your proofs as well. If we're returning this on requests, if this is synchronous, again, we're going to be able to have these strong offline proofs. We want to enable batching. And this is a balance between very quick responses to clients, but also enabling witnessing and being able to handle high volumes of traffic. Our goal is it's not O of milliseconds, it becomes O of seconds. We don't have to go to O of minutes. And a lot of this is going to be experimentation and just seeing how this works in a real world deployment using, again, I won't spoil too much, but we'll talk a lot more about witnessing later, just starting to test some of this out. We'd also like to simplify the API, centralizing around the key types that we have found to be necessary in order to record signature events, and also simplify the number of verifiers, primarily focusing around public keys and certificates. Again, we can expand this over time if we see a need for more server-side canonicalization over client-side verification, or sorry, canonicalization. And the last point here is, again, very, very applicable to every ecosystem, which is the need for more logs. Right now, we have this one community-operated log. We'd simply like more logs. We want more log operators. For each log operator, we want to ideally have more logs that they run for redundancy. One of the other areas we'd like to explore is logs sharded not only temporally, but also by domain. This has a lot of benefit from the monitoring side of things. Right now, let's say that you're a developer for PipePI, you're recording your events, but as you're monitoring, you're also getting events that are coming from the NPM ecosystem or from the RubyGems ecosystem. If we have sharding by domain, it's going to make it a lot easier for monitors. Alrighty, so that has been an overview of how we use transparency logs and the learnings that we've had. I'll quickly plug SigStoreCon. So we're actually going to have a co-located event focused on not only Sigstore, but other supply chain projects like Salsa, SBOM, Tough in Toto. This will be co-located with KubeCon in November. If you're interested in coming or learning more about the event, you can scan the QR code or feel free to ping me if you're interested in hearing more. Alrighty, thank you very much.
I hope there's going to be advertising fee.
Question, yes.
In your model, you showed one transparency log for record and a database. So if I understood correctly, the database is for pushing like Salsa artifacts and stuff like that, right? Salsa attestations for the artifact and like vulnerability and stuff like that. Is that right?
So this database is for storage of the tree data. So Trillian uses it for storing its leaves. The other usage of it is for the search index as well. This is a detail of the system. For the attestations, we are actually storing them in Google Cloud Storage. Again, this is, I think, one of these points about making this more modular and being able to split this apart. Yeah. Ideally, if you want each of these components, you can put them wherever you want. But ideally, we're going to have one database for each of these
Is there components. A kind of roadmap or a kind of thought process where you would link your artifact with the attestations or proofs for the attestations as well to be transparent?
Yeah, so this gets into a bit around Salsa and around build process. So a lot of the ecosystems actually haven't adopted just Sigstore signatures. It's that Salsa provenance is signed with Sigstore. And this actually gets into one of the points I made around signing with workload identities. So as a really, really quick high-level overview, the way this works is that a lot of CI systems have identities. So for example, GitHub Actions, each workflow has an identity. You can use that identity then to do this Sigstore dance where you're going to fetch a certificate and then use that to sign your build provenance.
Hi, question. In City, we have kind of a challenge with the domain owners not monitoring the logs. And you have kind of a similar challenge here with maybe users not monitoring their OpenID identities. So my question is, do you have any experience working with users and how they're like perceiving this new way of monitoring and insights you can share?
That's a really great question. And I will say, it is an area that we are actively trying to figure out how to make easier. So we have a tool to do this. Users can choose to run it if they want to. I'm going to guess probably not a lot of users do so. I think this is one area to look at. Package registries could run these monitors for their users, for example. I'd love to see a system like Have I Been Pwned for this. I think the CertSpotter project is a great example of something that makes this easier as well, that this becomes a service that users can subscribe to get these notifications. But I would say it's an area that we know that we want to see more adoption. And again, I think it's one of these things that's across ecosystems as well.
Okay, we'll take one more question. Jon, I can ask you to get set up.
Yes. So trust policies. Obviously, in order to get the full benefit of transparency technology, the trust policy needs to fail closed, which of course implies concerns about miscontinuity for both log operators and witnesses. Do you have any users that fail closed on Sigstore right now, and the ones that are not, are they well, how do you see that? What are those discussions like?
So it's a really great question. So I think one example of that would be around the homebrew adoption. So I guess to add some context here, the verification side of things, it's ultimately the decision of the user or the ecosystem on do they want to be failing closed or open. And I think homebrew is a good example of that. So they're still in beta, so it's not a hard failed close here, but you could see over time, they have the trust policy. They know who is the right signer for a given artifact. So ultimately, it's something where, again, if this is a fully offline process, I do think that they could move towards a fail closed system. One of the other interesting projects, there's a PEP in the Python community called PEP 458. Roughly, it's about mitigating package registry compromise, but one way it can be used is to distribute trust policies of these mappings between identities and artifacts. It's an area where we're still kind of actively exploring, but I think it's a nice way to start seeing some of these technologies fitting together, where you can have these mappings and then ultimately, given the system's offline, it should be able to be fail closed.
Okay, let's do a round of applause for Hayden. And Hayden is around and he'll be leading the binary transparency session tomorrow, so feel free to ask him more follow-up questions. All right, we do have a lightning talk between you and lunch, but it's a good one. So I'd love to welcome Edona talking to us about digital identity. Please give her a round of applause.
Thank you. So my name is Edona, and I would like to start by apologizing for the dramatic decrease in expertise level from the Google people. I'm a researcher at the Graz University of Technology, and I'm passionate about these two topics, so basically digital identity and transparency systems. And I'm passionate about finding ways to integrate them with one another without breaking any of the guarantees that both systems provide. So just a quick introduction into user-centric digital identity frameworks, and especially on verifiable credentials. Just to get all of us in the same page, when I'm talking about credentials, we're talking about means to prove who you are online to different service providers. And there has been this in the past few years, and also on a national and also European level and also global level, this paradigm shift of rather having your identity scattered through all of these service providers and kind of losing control of where your data is going to more of a user-centric. So now you have all of your data in some app in your device, and now the user is in control of which part of this data to share with which service providers, and also even more privacy-preserving ways of proving to some service providers some attributes about you without showing the actual attributes. So what are the main actors? So we have some symmetry to the CT ecosystem. So we have some authority, which in our case are the issuers. And these issuers issue some credentials to a user. And this user saves and manages these credentials on this wallet application, digital identity wallet application. Further, this user presents these credentials in order to access some service of some service provider or a verifier. And the catch here is that we do not get the issuer to learn every time we're trying to log into a service provider. So what if we want to enhance this digital identity ecosystem and add some transparency layers to it? How could that look like? So this is a generic framework which is applicable to other ecosystems as well. But basically we would have this source or this authority which would log stuff in our transparency logs. And in our case, this could be either the issuer, which would log every time they issue a credential. This could be the verifier, which would log every time they are consuming this credential. Or this could be even wallet providers, which are the developers of the wallet application itself, which are publishing their binaries into this transparency log. And then we would have, of course, the tamper-proof append-only log in the center. We would have the consumer of this log, which again could be, depending on the application, could be several actors, either the verifier or the end user, and so on and so forth. Of course, we still need this all of this ecosystem of some way to publish digests of this log, and also to make sure that these logs are growing consistently, and the auditors that help verify those proofs and ensure those transparency guarantees. So how can transparency technology help? Of course, this is the case with other ecosystems as well, right? We get increased trust and accountability, and we ensure that the data that we're relying on can be trusted, and we detect if something has gone wrong. Basically, if some credential has been issued on behalf of me, but for somebody else who could impersonate me. And we also make it easier for auditors, in the sense of legal auditors, to automatically verify that an actor has been behaving correctly. And we also go more into this user empowerment lane, where we now give the user visibility of what's actually happening with his own data. But of course, the translation of these transparency principles into the digital identity context is not so straightforward, because we're dealing with highly sensitive data. So now we still want to maintain this public verifiability of the data that we're relying on, but we are dealing with private credentials and highly sensitive data. So we are running into the risk of actually having the risk of leaking and enabling some user tracking and correlation by having data being appended to these transparency logs. And these are the main issues that need to be solved when trying to adopt transparency logs for digital identity ecosystems. So I'm going to go into the main phases of the life cycle of a wallet, and also like a digital credential, and see which transparency principles can be applied into which of these phases and how. The first one that comes to mind, of course, is wallet binary transparency, especially after the talk and after seeing that these software supply management attacks are on the rise, and considering how sensitive the data that the wallet that's managing is, we need some assurance about the legitimateness of the binary that we're running, basically, because that's the cornerstone, that's the main tool that the user has to manage its own credentials and show them to the verifiers. So, of course, that's helpful in preventing tampering and malware, and also validate open source, and it gives us trust that these updates are logged somewhere, publicly verifiable, and no malicious update has been swept into the update of the wallet app. And this there's also some implication here, like this could also be beneficial for the issuer, because also the issuer, before issuing these credentials to the user, he needs to have some assurance that the wallet that he's going to issue the credentials into is benign and is trustworthy. During the issuance, so going with the trend that we maintain the ecosystem as it is, but we build a transparency layer on top, we try to make the issuance process as less disruptive as possible. So now every time the issuer is issuing a credential, at the same time he is, the issuer, it is publishing some record to this transparency log about the issuance of this specific credential. What's the challenge here? Of course, we have sensitive personal information and that these transparency logs are public by design. So what are our goals when trying to build such a credential transparency system? First of all is we want to maintain the credential privacy. So we do not want to leak anything about the sensitive data that we're trying to issue. And also, if we have multiple credentials pertaining to the same user that are being logged in the same transparency logs, we want these entries to be non-related to one another. And because just pushing stuff into a log is not enough, we want that to be discoverable by the user. So we want some mechanism for the user to be able to identify all the log entry data that are pertaining to him. And we also want some way to enforce this logging. And that is a concept that we called verifier verifiability, which is how can the verifier be ensured that the correct credential for the correct user was logged into this transparency log. And we employ 3 building blocks when trying to solve this problem. Of course, on the center we have this append-only tamper-proof log. We have some blinding mechanism. Of course, we do not want to publish the credential. And we also employ some zero-knowledge proofs. So during the showing process, so when the holder is now showing a credential to a verifier, in order to enable the verifier to enforce the correct logging of this issuance, we also proof to the verifier, but in zero knowledge, so without giving him any extra additional information about our identity, that the blinding mechanism that was used when publishing to the log and the authentication mechanism that are using for this verifier both pertain to the same user ID, but we're not showing this user ID, this identity, this core identity of the user to the verifier. And yeah, we also have developed protocols for all of the 3 phases of credential issues, showing and discovery for that, and also done some initial evaluation and showed that it's feasible, even considering like a growth rate of similar to the certificate transparency, which is not the case for credential transparency systems. It's feasible for the user device to do this background monitoring of has this issuer issued a credential on my behalf, and is this genuine or not? Going on to the next stage, so presentation. So this is a different problem setting at the design space. When I try to think of the mental model of that, it seems somehow more similar to key transparency to me, rather than just having a log of events of issued credentials. So we need to differentiate between 2 different design spaces. So we can either have device stored credentials, so credentials stored on the user device, and also the key material that's associated with that, which is not always a good idea. And then we can also have like the possibility of having a remote credential management system. And especially in the latter case, we need to have some transparency guarantees that this remote credential management system is not showing a credential on behalf of the user without the user knowing that. So what would be the goal of such a credential presentation transparency system? The goal would be the user to be able to audit all presentations that are made on the user's behalf. And we still need to preserve the privacy and usability features of the system. So there are 2 ways to go with this. We can either go fully privacy preserving or less strict assumptions and say that we are preserving the privacy level of the underlying digital identity ecosystem. So if it's SSO or something, we are not leaking, we're not making privacy worse, basically. And there is also another perspective to this one. So the verifier, generally when doing this presentation process, asks for some attributes for the user. And the user has no means to verify whether this verifier is actually can ask for all of these attributes. So if we provide some sort of transparency to the presentation process, there's also some audit trail of was this verifier actually accredited to ask for this many features, or did he over-ask and we basically shared part of our private data without needing that. And finally, revocation, which is, I like to think of revocation as the gossip of transparency system, because there is no good solution for that, and it's messy in digital credentials. So generally, at least in our world, it's kind of swept under the rug and not dealt with in most papers. So during the presentation, verifiers need to confirm, of course, the status and the validity of the verifiable credentials. But when we're doing this revocation checks, we run into the risk of having traceability and linkability when we're trying to basically audit, to check the status of this. And there have been proposals. One of them is to have 2 trees, so basically one for issuance and one for revocation. So now when we are presenting a credential to this verifier, we give both a proof of membership that it has been issued to the issuance tree, and then we also a proof of non-membership that it has not been revoked, meaning that credential is still active. Another approach is the one that Facebook's auditable key directory takes, which is to have a single tree, but now we are marking this revoked credentials or keys in their case as stale, but by having that as an input to this verifiable random functions that determines the index of the entry. And yeah, that was all that I had. If you have any questions or even more welcome suggestions, I'm open for those.
Great, thank you very much, Edona. We'll take questions for Edona at lunch, so I think we're going to break there. You've been a great audience, so let's take a full hour and we'll resume at 1:15 and pick up with some witnessing. Thank you very much.
Yeah.
Okay, welcome back from lunch, everybody. Okay, up next, we are having it's either, you can look at it as a mini summit or a mega talk, one of the two, but one of our key pillars is witnessing. So we're going to go deep into witnessing. And for that, we have a whole set of awesome folks. And we're going to kick off with Martin Hutchinson. Please welcome Martin.
Oh, thank you. It's me again. So I'm pleased to kick off this mini conference or mega talk. So mine's going to be the first of 4 related talks, which is taking us on an adventure from witnessing through to implementing, and then finally with verifying secure transparency ecosystems. So there's going to be a lot of pictures that aren't of the armored witness. So this is the armored witness here, and there's also one of them here. That's what we're going to be talking about. But you're going to see a lot of other pictures that look a bit irrelevant as we go through. So before we can talk about the armored witness, we need to talk about witnessing. And before we can talk about witnessing, I think we all need to have a shared understanding of what logs are. Hopefully there's nothing on this slide that seems novel to anybody, but we're going to just go through it because it's kind of important, right? So a log provides a verifiable, globally consistent, append-only list of data. Which means, obviously, once data is added to the log, it can't be deleted, nor can it be modified, and new data can only be added to the end of the log. So that's append only. Globally consistent means whoever comes to the log, wherever they are in the world, and whoever they happen to be, sees the same list of the data in the log. And verifiable underpins all of this. That's what logs are about. But verifiables gets thrown around, and it's an interesting one, right? There's a huge difference between verifiable and verified, and that difference requires a verifier to address it, and that's where witnesses come in. So witnesses, that is an measure in a tree, if you believe it or not. So witnesses, a single witness can check that a log is append only. So how it does it, the first time a witness meets a log, it gets a checkpoint from the log and says, cool, I'll take note of that. It signs that checkpoint and then says, from here on out, I'm going to hold you accountable that any other checkpoint I ever sign is going to be consistent with that checkpoint. So it's going to check the append-only property. So it keeps that checkpoint safely, locally, as safely as it keeps its key material, because if that could be swapped, then it could be tricked into signing a split view. And then as time progresses, it gets hold of new checkpoints for that log, it gets hold of consistency proofs for that log, and it verifies those, ratchets forwards, and it will sign the new checkpoint. And then at that point, it can throw away the old checkpoint because the new checkpoint commits to that. So it only needs a sort of finite constant amount of space in order to witness each log. So that a single witness gives us verification of this append-only property, but the globally consistent property requires multiple witnesses. So one way of looking at it is the more witnesses that you have that have seen the same thing, well, the more you can trust that is the view, right? And you can strengthen that further with a finite pool of witnesses, and then using a quorum technique, so N of M, to guarantee that the log is globally consistent. So that's a witness, and you can see now it's verifying what we just talked about, what logs fundamentally are. But I think it's also important to talk about witnesses, what witnesses do not do, because they don't solve every problem with or every verifiable aspect of logs, right? They do not download any of the leaves from the log, so they're only concerned with the internal hashes, so the Merkle tree structure, and the append-only nature, so that they are not going to be downloading, say, firmware from your firmware transparency log and checking that that's legit firmware that's been verifiably built or anything of the sort. So in your ecosystem, you're going to need another verifier, often called an auditor or a monitor, so that you'll need that bespoke to your ecosystem, most likely, to make sure that what is in the logs is actually legit. But the witness can underpin all of this by making sure that everyone is at least seeing the same view of the log. And the other thing about witnesses, I think this was touched on earlier as well, is that witnesses, they don't provide checkpoints directly to end users. In fact, witnesses are usually kept off the addressable internet. One that avoids a whole bunch of security risks if they can't easily be accessed from any bad actor, can't just point at where they are. But also it's just a scaling point of view. Witnesses should be cheap to run. And if you're going to be a witness that monitors tens or hundreds of logs, and each of those logs has thousands or millions of clients, you can easily imagine that scaling a witness to meet the needs of all of that read traffic would become really expensive. So for that reason, we need another way to get these signed checkpoints from witnesses out into the world. And we'll talk about that later on. So that's witness. The Omni witness is a step up from the witness. It's the name that we use for the Trust Fabric witness. So we have a witness that anybody can run that's just out there. The Omni witness is basically that with a policy. And the policy is sort of twofold. So at one level, it says, hey, like these are the logs that it currently verifies. And there's a list of them there. I'm not going to read it, but if you see your name on there, feel proud. And the other part of the policy is explaining how people that bring up their own log today can be witnessed by the Omni witness and how to update that configuration. So the Omni witness can be run directly, so you can just check it out from a repository and go run it, or even better, package it up with some kind of container ecosystem like Docker. And there was a period of time where we thought, okay, this Omni witness, this is how we're going to kickstart the witness ecosystem. And so that's what we did, and we had a number of participants running the Omni witness, and it worked for a while. But the sort of real problem that we got with it was really about software updates or policy updates. So if a new log was added, it didn't immediately trickle down, and it didn't get into everybody's running version. And what it turned into is kind of how a lot of this stuff turns into is us nagging people to update their software. And Al probably remembers this quite well, of just like, please, come on, I know we asked you last week, but can we do it again? Can you please update it, because there's a new log today? And so we knew we were onto the right idea, the right sort of shape of things, but it needed a bit more work to get it to the point where this could be a sort of viable, scalable witness network that people could depend on. And so the Armored Witness was born, which is basically the Omni Witness with a suit of armor and packaged up in a little plug-and-play device that looks like that. So I don't want to ruin all the details about what it is, because that's why Andrea and Al are here, to ruin all those details. But the summary of it is, it's a custom chip that's living inside there, and that chip is open source. And when you get one of these, you should verify it. But if you just trust us, don't, but you could just trust us, and then you can just plug it in with power over Ethernet, and you just sort of feed it power, you feed it internet, and it will just do everything for you. So on the first boot, it's going to update itself to the latest version of the software and keep doing that periodically, so we don't have to be nagging anybody. The software that it downloads comes from a firmware transparency log, and it makes sure that any software that it runs every time it boots up is both signed and available, is committed to in a firmware transparency log. So it secures all the logs out there, but it also makes sure of securing itself, which is pretty neat. But again, Al and Andrea are going to go into more details on that. So what we have at the moment is, I think, I don't know, maybe a dozen or so, is that right, of these armored witnesses out there? 14 and a half. Let's say a dozen of those armored witnesses out there, right? And one way of looking at it is like, that's great, we've got 14 different witnesses, and depending on your threat model, you might be happy to take it on that basis. But another way of looking at it, and the more conservative, and I think, in the security space, that's a good attitude to have, is that it only counts as one. It's just one witness, really, because it's the Trust Fabric's reputation, that we're sort of staking on this, and we just have people running this on our behalf. And then you think, well, if we're only going to have one reputational unit, basically, depending on this, why have you gone to this effort of having a bunch of devices all around the world with custom hardware and all of this stuff? You could have just taken the Omni Witness and run it on a Raspberry Pi, right? Like, that would have been just as good. And that is a very good question. But luckily, I think we've got a good answer to it. Hopefully, can convince you all. One is that by having so many devices spread geographically, it means that we get good global coverage under this single reputational unit. So one way that one might imagine that a log could present a split view would be geographically. And so the more regions that we can get covered, the more likely we are to detect that happening. And the more likely it is to be detected, the less likely a log is to do it. Another important thing is it holds us accountable. If if what I was doing is just running this in a Raspberry Pi in my bedroom, that'd be wicked, right? But the other thing is I could just pull the key material off there, and then I can, like, just for the right amount of money, I'll not say how much it is, but you can, I'll just sign other split views of things, and people wouldn't be able to tell the difference with that. But the only way we can get, I'll talk a lot more about this, but the only way we can get updates onto there is via a transparency log. And so that looking at the transparency log tells you everything that's happening on these devices, and that's like a really neat feature. Another part of it is by having a lot of people, these in the hands of a lot of people in different ecosystems who are all passionate about their logs, but might not have otherwise before, now thought about witnessing. They're now thinking about witnessing. So there's a kind of awareness part of it. And then I think the part of it that I'm the most proud of, and I think is the coolest, is because it's the right thing to do. We really obviously believe in transparency, and this is now a living example of everything that we've learned from the collective, like over a decade or whatever, that we've all been working in transparency, put together in an end-to-end firmware transparency solution where every part of it is verifiable and verified. And I think that's super cool. So that's a kind of a high-level overview of what the Armored Witness is all about. And I say we've got other speakers who are going to come in and talk more about that. Quickly now kind of going into like, how does it work? Rasmus talked a little bit about this earlier, about the Bastion, and so I better talk about it because he said I'd talk about it. So there's two ways that it works. There's a synchronous way and an asynchronous way. So the synchronous way, this is sort of the more modern way that we expect things to move in this direction. What happens is the witnesses on startup, they will dial into a Bastion and leave a long-lived connection open, basically, and say, hey, Bastion, if anyone comes to you and wants me, you can use this connection to find me. Meanwhile, logs are kind of doing their thing, and they want to create a new checkpoint and share that with the world. What they do is they dial into the Bastion and say, hey, here's my new checkpoint. Here's a consistency proof. Can you get me a bunch of signatures from that? And they send that out to the witnesses that are sort of secretly dialed into the Bastion. They get that information back and they send it back to the log. The log's super happy because in real time now, it's got hold of a bunch of witnessed signatures onto its checkpoint. And then users are happy because they can just dial into the log as they normally do. And now instead of just getting a checkpoint with a log signature, they get the log signature and the witness signatures on there. So the Bastion is covered by a C2SP. Yeah, I said it right. C2SP spec, and so that's all there, and other people can integrate with this on either side or write your own Bastion if that's your jam. But because we're also trying to bootstrap this and go from like 0 witnesses in the world to kind of having 1 witness in the world, there's kind of this sort of legacy sort of thing going on, right? There's a lot of logs out there that don't know about witnessing and so don't know about the Bastion and aren't supporting any of that path. And so that we can kind of get those logs witnessed, this is why we have it so that the witness can also work in this asynchronous kind of mode where they basically go to the log as just normal clients of the log and say, yo, can you give me a new checkpoint and how about a consistency proof with that? And then they do their thing locally. But then you've kind of got a problem, right? Because the log does not know about witness signatures and isn't interested in them yet. The witness is secretly hidden away in the world. So how is it going to get those checkpoints out there? Well, that's why we have the distributor, which is basically working as a way of getting these witness checkpoints out to users. So yeah, the distributor, essentially this is just a bootstrapping thing, right? If everyone moves over to Bastions, we're kind of happy to turn all of this stuff down. But what the distributor does is just receives these checkpoints from witnesses, merges them together, much as the log was. So if 10 witnesses all come in with signed checkpoints for the same checkpoint, the distributor can serve this single checkpoint with 10 witness signatures on it, which is kind of super neat and efficient for clients. And that's basically it, right? And so if this grows and becomes more load-bearing for any reason, we'll make it a spec, but it isn't at the moment. But it is, we've got one running, the code is open source, and the API is just kind of RESTful API where you can just make simple requests to it. And there's a little thing here showing that you can just, we've got a client in the repository, which you can just kind of call into it and get some checkpoints out, and it inspects the checkpoints and the witness signatures in those checkpoints and tells you kind of how fresh they are. So, to recap, before I hand over to Andrea, Yeah, the armored witness, it's a lightweight plug-and-play device. So you get it, you plug it in, feed it internet power, and it will just take care of itself with very little effort from you. Just please keep it dry. The goal of this is to kickstart a diverse witness network, right? So we're going from 0 to 1, and I think that's probably the hardest change. Hopefully going from 1 to 2 and then beyond should be a lot less effort for people, and you don't need to be doing anything with custom hardware and firmware. Like, if you're happy to stake your own reputation on this, and you're prepared to run things with good OPSEC, then you can do this using, a personal computer or something. You don't need this fleet of devices that you're going to be managing. It's resistant to tampering, or at least it's very evident if we've been tampering with it and we've been putting bad firmware updates out to it. People can see that in the log. All of that stuff is verifiable, and we verify it, but we ask that other people also run verifiers for it. And again, this serves as a showcase of everything that we think good firmware transparency, and indeed just end-to-end transparency securely done, can be. All right, so that's the end of my part of the talk. If there's any questions immediately related to this, we could do them, but otherwise I'm just going to hand over to Andrea, and I think it might make sense to do questions at the end. There's always one.
How is the key managed on this witness, and when is it generated?
Yeah, Andrea is going to talk about this.
Perfect.
Yeah.
Quick one. The verifiable firmware transparency. What does it actually mean? Does it just mean checking the ledger for the entry? Sorry, I will answer that.
Yeah, I was going to. He asked the question. It's a good question. Luckily, we've got a good talk for it as well, so don't worry about that. Right, it seems like okay. There's one more, and we'll try our luck there and see if someone's going to ask a question that's not covered by the next talks.
So you mentioned multiple people having these devices around the world.
Yeah.
How do you distribute them? Like, how can I get one?
Yeah, Al can speak. Well, do you want to speak to Al's basically been shipping them out. I don't know if he's been taking... Yeah, he is the distributor.
If you want one of these devices, not an armored witness device, but one of these devices, you should talk to Andrea, because he will sell you one. You can turn one of those devices into something that looks a lot like the armored witness, and it would do the same job, but it won't be an armored witness because the armored witnesses are specific devices that we've provisioned and sent out to some people that have very kindly just agreed to sort of look after these devices.
Cool.
Thank you. Should I just do the arrow keys? Yes. So, thank you. Really glad to be here. So I step in to answer the question, how can I provide the best possible hardware and software framework for these fine people to develop their own firmware. So we don't have much time, so just very quick introduction about myself. I work for WithSecure, security auditors, engineers, and I'm the creator of the USB Armory, which is the originator for the modification that ended up being the Armory Witness. So the USB Armory is a piece of open hardware and also software that accompanies it to handle and manage the device, which was born a few years ago. This is the second version, and basically it's this tiny device here, has a USB plug, USB receptacle, and the idea is that I wanted to put a powerful system on chip in the tiniest possible form factor to use it as a really powerful, secure enclave. And so this project, the existence of these projects is also what I think gave the idea to create a modification that would be suitable for these needs, because the point of this device has always been to be transparent as possible, as verifiable as possible before even I knew about this effort. And so I think it was a very nice pairing between the work that I've done with this device and the work that is being done right now with all of this ecosystem. So the idea here is how we can build a witness that we can trust with high transparency, low touch and maintenance free. This is really important. It needs to be something where you don't need to manage updates, you don't need to manage the operating system, you don't need to have a complex supply chain for what you're going to put on it. And that it can also demonstrate at the same time all of these principles of binary and firmware transparencies that are being promoted. So the goal of this device, open hardware, open software as much as possible. Correction on the earlier talk, the chip that's on it is not a custom chip, it's a commercial chip, but that's the only thing which is a little bit opaque, and I'll talk about it, how we can mitigate that. The rest is completely open. You can download the schematics, the PCB layout. You can even rebuild it yourself if you have a fab. So it's all as open as possible. We want to reduce the attack surface as much as possible, and I explain exactly how we're going to do that, and it needs to be plug and go. You just plug it in, and it just works. So we're combining 3 things that I co-authored to support this project. The USB Armory itself, a framework that I call Tamago, which is, I'm going to explain in detail what it is about, and Goatee, which is a library which has been created with Tamago for the USB Armory. So first thing first, we need to change the form factor of this device. So we transition from this piece of hardware to this one. So we basically swapped one of the USB ports with a power over Ethernet RJ45 Ethernet connection. So now in order to power this device, you just plug in a power over Ethernet cable and this device will power up and boot. So this is the first modification that was being done. The rest remains pretty much identical to the original USB Armory, which means we have an internal storage, an MMC storage of 16 gigabytes. We have an external secure element, which is unused in this specific application, but it's there. The system on chip is a pretty powerful system on chip from NXP. It's a NXP. It's a 900 megahertz Cortex A7. We have Ethernet on board with power over Ethernet, and we also have another USB port, which also is going to be important for the verification of this device. The tooling to build firmware, to fuse keys on this firmware, to verify this device, to load firmware on it is entirely open source. So even when there were tools available from NXP that were somewhat opaque or not really good, we completely re-implemented them as open source tools. So it's, except for the system on chip itself, it's as open as possible. And it's also one of the few chips where the mascaron, despite being a binary blob, it can actually be read and reverse engineered for the purpose of trying to understand as much as possible if there's any surprises in the device. There's a number of security features on the device. So first of all, there's a secure boot. So we can provision keys on the device permanently, so fuse them, so that the device can only accept firmware which is signed by the corresponding private keys. And this is important. These are not vendor fuse keys, but they can be fused by the user. So in this case, the Armored Witness maintainers. If you get your own device such as this, you can fuse your own keys. You're getting into an open state, and then you can lock the unit with your own keys. There's cryptographic accelerator on board, which also provide full memory encryption. So the external RAM on this device is 0.5 gigabyte of RAM. It can be completely 100% encrypted with a key that just lives on the system on chip. And this is also important for against specific tamper-proof attacks. There's a unique key per device, which gets unlocked once the device is secure booted. So that's why the main key derivation happens. Each unit, once secure booted, has a unique key which is fused at the moment of the secure booting. It's random and it can be derived every time it's booted. And then we also have replay protected memory block on the MMC. So we can have an area of the internal storage, which with a shared password between the system on chip. Again, we derive it from this secret, which is only unlocked when the device is secure booted. So we can do authenticated read and writes of specific regions on the MMC, and also with a protected replay counter. So this prevents rollback attacks. You cannot desolder the flash for one unit, let's say with an older firmware version, and put it back on the same unit, the system on chip will know that you're trying to execute an older version of the firmware which are not supposed to run on that device. So it prevents specific rollback attacks. Now, how do we want to put firmware on this device? So traditionally, the way we have been doing firmware on these devices, I do embedded systems auditing, so I also audit a lot of systems that are like this. In such a system, you would have your system on chip doing secure boot. It would authenticate the bootloader. Typically, it's U-boot in this kind of system. The bootloader would have another set of keys. It would need to boot Linux and authenticate Linux. Then Linux would have to derive a key using its own drivers, decrypt the file system, and then it would run your application. Now, that's a very big attack surface. There are many, many dependencies that are involved in setting up all of these chain of trust. The bootloader Linux, as we know, especially the bootloader part written in C, so languages which, as we know today, they're not considered very safe in terms of security. We found many CVs, and of course, many others found many CVs on U-boot. And of course, when you need to maintain the chain of trust on an embedded device, that's the first part that you're going to attack, because the hardware will authenticate the bootloader, but if for some reason you can exploit the bootloader parsing of the Linux kernel, of the flash contents, of the signature, then if you broke the chain of trust, you can get access to this secret which is present on the system. So we want to reduce the attack surface as much as possible and reduce maintenance. If we have to maintain updates for the bootloader, for Linux, for its entire runtime, it's a very complex environment to eventually run probably a monolithic Go binary of a few thousands lines of code. And so we, you know, in all my career, I realized I created this hardware, and then we were creating firmware in this way. Let's say you have a cryptocurrency wallet or any other sensitive application. You feel that even if your code is nice and elegant and secure, you are basically surrounded by a hostile environment in terms of supply chain and security. And so we wanted to kill first of all, to kill any C code from this chain of trust, and reduce the attack surface in this supply chain as much as possible. So what the Tamago framework does, removes any runtime dependency on C code, and also removes any need for an operating system or the operating system runtime for executing Go code. And this is the framework that the Armoury Witness is based on. And so basically what Tamago achieves, it basically puts the Go language on the left side of this chart, because it brings it to the bare metal in the same level that C and Rust are, while maintaining 100% compatibility with the language, with the libraries, with the ecosystem as well. So that's the idea of Tamago, to give another choice for creating firmware at the very low level. Of course, someone think there are unikernel, there are library OSs that somewhat they try to do the same thing. You have these frameworks where you can just take your application and a unikernel is created. But what these frameworks do most of the times, they just shift complexity away. They hide you from what is actually happening underneath, because at the end you're going to have a real-time operating system maybe, or some other OS which is hidden from you, and it's unsafe. It's written in C. It has even less chances of being updated. So these kind of projects, they don't meet the goals that we have in mind here. We want to completely be free of any of such dependencies. So what Tamago is a minimally, this is important, it's a minimally patched code distribution, because we want to achieve trust with this entire ecosystem. So it's not something that is done with spaghetti code, with a very complex reimplementation. We're talking about 5,000 lines of code, which extends the original Go support to another Go OS platform, which is called Tamago, which can go on the ARM and RISC-V architecture and allows you execution of Go on the bare metal. And everything else is implemented just a regular Go package that you can import. Again, 5,000 lines of code. The patch is readable. It's easy to follow. If you're interested into this, in the next days I can also go through the all modifications. I think it's also a very good way to understand how the Go compiler works, and but also about how the hardware works. we reuse a lot of code from existing architectures within the Go runtime. So also for all those 5,000 lines of code, the number of lines which are actually original and new are probably only the files at the bottom. So we're talking about probably less than 2,000 lines of code of completely new and fresh code which is being implemented. And so what this allows us to do is to use Go as you would use on any conventional operating system, but we're close to the bare metal. So we can write drivers in it. We can write peripheral drivers in Go because we can read and write register. We can do direct memory access with a package that we have. And you might think there are a lot of unsafe imports in all of this. It's just 3 of them, and they're very isolated and very specific. So it's also done in a way where it's also very difficult to create critical bugs in implementing this code. And the application is never ever required to use any unsafe function. So we basically transition from a layout where we would have our user space, the Go runtime running in user space. We would have the operating system. We would have the drivers in the operating system, and then we would have a bootloader. Now we don't need any of that. We just have a single Go runtime running on the bare metal, where the drivers are just libraries which are imported in your main Go application, and we also don't need a bootloader anymore because Tamago built binaries, they can boot on themselves. They can do the hardware initialization. It's just one import. Developing, building, and running is identical to the compilation of any Go application. You use Go build, you import the board support package as you would any Go package, and then the hardware is just exposed as regular Go functions. And this also means that we maintain, and this is really important for this application, build reproducibility. So we maintain the same properties, we maintain the same Go module support, all the ecosystem is maintained. So your software bill of material for the entire software that runs on this device is in the Go mod file. So the same properties are maintained. And also what I really enjoy is the fact that I can now develop complex low-level firmware for such a device just as easily as on Linux, Windows, and macOS, because specifically the Go ecosystem makes it easy to do. And speaking of attack surface reduction, drivers written in Go using Go routines, channel, mutexes, and all of this, the line of code count is dramatically reduced in this context. So you see here the network driver, the Ethernet driver is 400 lines of code. The cryptographic accelerator driver is 840 lines of code. The MMC driver, so the flash driver, which is probably one of the most complex ones because the specifications are a nightmare, is 1,100 lines of code, and also the USB driver is pretty much the same. So we reduced a lot the attack surface of this. I know by memory when I receive a package on this device or a USB command, I can cycle in my mind of all the calls that it's going through, and that would be impossible with the Linux kernel. So now we can create true unikernels, true library OSs, and a single Go binary has everything that you need. And we eliminated C. There's not a single line of C code involved from the moment the system on chip jumps to the application, which is also the bootloader. There's not a single line of C code involved. I will demo this if you want. In these days, approach me during the break. I can show you all of this. Just one example on how we use this. My own personal smart card, this is of course all open source, is a Tamago application. So I plug in my USB armory, and I have a smart card, an OpenPGP smart card. It's also a UTF FIDO token. And what we can do with this framework is that we can mix layers that traditionally are very hard to mix together. So I can SSH into my smart card to unlock it, instead of sending an unsafe APDU command with the pin which goes on the clear on the USB bus. And the same firmware can handle TCP/IP, SSH, but also the low-level APDU things. It's all in Go code. And these are things that if you try to do them in C on a regular smart card, they are impossible. If you try to do them in a real-time operating system, it's also becomes difficult. Here, it's just a matter of importing the right Go libraries. It becomes really easy. We even created a bootloader with this. So we can boot Linux with a bootloader which is written in Tamago. So you can perform very low-level operations. Again, 700 lines of code for the bootloader. So we have the hardware. We have a framework that allows these fine gentlemen to put Go code on this device. We need a third component here, which is a trusted execution environment, because this is potentially just one of the applets that can run on this hardware. So we want to have some sort of control, and to reduce the attack surface, we also want to to delegate the most complex tasks to an isolated environment. So we created a trusted execution environment entirely also with this framework, which is called GoT, which allows to supervise, to monitor applets or even operating systems such as Linux, or applets written in bare metal C, bare metal Rust, or bare metal Go, and to give them an API that allows them, for instance, to do key derivation. So the idea is that if you have more than one applet, you can derive keys which are different, which are diversified for this applet, and the applet cannot break from that execution context and derive the key that the other applet is deriving. This is traditionally on Linux, you would use OPTEE for do this kind of tasks. GoT does exactly the same thing, but completely in memory safe code. So to build a hardware witness, we combine all of these properties, and we created, first of all, a bootloader. So the only reason why we have the bootloader is because we encrypt the entire memory for the operating system and the applet. Otherwise, the bootloader part would not be needed. We cannot enable memory encryption and then proceed into our normal execution. We need to stage this approach. So the bootloader only exists to enable memory encryption and then jump to the operating system. The operating system is what supervises the applet. It has, for instance, the replay protected memory block API. It is the one that derives the key that allows authenticated read and writes with the flash memory. It has the Ethernet driver, and it handles the key derivation for the applet itself, and it supervises the applet. The TCP/IP stack, for instance, which is gvisor because it's in pure Go, lives in the applet itself. So this is a way to split the attack surface and to have the most complex attack surface in the most isolated level. So we have an API with sort of system calls between the applet and the operating system to receive and transmit Ethernet packets, but the actual TCP/IP stack lives in the applet, and the Omni Witness code, the Armory Witness code, lives in the applet itself. This also allows to update the applet in a manner separate than the operating system, and also to have signing strategies that, if you want, they could be different. You can have different keys authenticating each of these components. So in this specific case, the boot ROM is fused with the keys from this ecosystem. It authenticates the bootloader authenticates the operating system, and the operating system authenticates the applet. And from the boot ROM, so the boot ROM, of course, must use the NXP algorithms for signing and authentication, but the rest, it's all using the ecosystem for the firmware binary transparency. Both the applet and the operating system can use regular Go packages to interact with the hardware because all the drivers are written in Go. So this is, for instance, the APIs for enabling memory encryption. Again, very few calls. This is how we load an ELF image, and then we just load it to launch. Again, it's all, you go to package, go dev, and you can find these packages, and you have all the API that is needed for driver. Replay protected memory block, there's a Go functions for that. You can program the key, you can read the counter in an authenticated way, and then you can read and write the different memory blocks. So this is how the operating system basically implements these calls that are given to the applet in their API. Key derivation, so you asked this is the call for the key derivation. So we derive a key unique for each system on chip with the functionality that NXP provides for creating blob encryption keys. So this is a call that is done at initialization of the applet. The operating system takes care of deriving the keys per applet request. This is the GoT API, so we can load an execution context and we can run it. And every time the execution context, in this case, is the applet, will raise an interrupt to make a system call, or because maybe an Ethernet packet arrives, then the execution context jumps back to the operating system, which can serve this call. So there's also full interrupt support in Tamago. So we handle interrupts like any operating system. To do RPC between the applet and the operating system, we defined an RPC interface, which basically uses in the end Go own net RPC, JSON RPC. So we just use that package, and we have system calls that allows to serialize and deserialize those calls, which I think it's a very nice way of combining something really low-level system calls, which something really convenient that Go provides. We didn't have to invent much, just pass this buffer, the length, and the rest is just done with JSON RPC. So the OS defines the functions for key derivation, checking if secure boot is enabled, or reading from the MMC, and these functions can just be called just like regular RPC calls from the applet. So it becomes really, really convenient. The trust anchor, so of course, is the boot ROM. Again, the boot ROM can be fused with your own keys, so it's not something fused with vendor-specific keys. There are no keys from WithSecure or from NXP here. And we re-implemented the library that does low-level USB communication with the device entirely in Go, so that you know exactly what's going on when the keys are being fused or when a firmware is being loaded. So in a nutshell, these devices, they can put into USB data loading mode. It means that when they're powered up, they're not running the firmware from the flash, but they're waiting for a firmware to come from USB. And this is as low level as it can get, because it's the boot ROM which enforces that protocol. The boot ROM is opaque, but we did reverse engineer it. We even had a third-party company doing an audit, so we did the best that we could to ensure that there were no surprises there. And so basically, when you're putting this device in USB serial download mode, you are so close to the metal and allows you to load your own verification firmware or to verify what is being run. And that's a trust anchor that we got. And I think Al is going to talk about also a tool that uses that. So in the presentation that will be published, you have all the links for everything. Everything is open source, the Armory, Tamago, GoT, and of course the Armory Witness. In the course of today and tomorrow, please ask me any questions. I can demo these devices. I can explain as much as you like. But I have to say it's been a real privilege for us to develop this new hardware and the framework needed to make your own firmware happening. Thank you. Do I have time for questions? If there are any questions? Yes?
Okay. Why is there a specific reason you took the extra mile of making Go bare metal capable instead of just using Rust, for example, in the first place?
Yeah. So first of all, when using Rust for bare metal, you cannot use the standard library of Rust. So this means that your ecosystem is much more limited in how you're going to implement things. And this specific kind of application requires using a fairly established and complex packages. You have the Node verifier. You have many libraries which are out there, and porting them to Rust would have been a huge overhead. In this way, you can just import them right away. Second, this is not a real-time application, and so it's really convenient to have the Go ecosystem features here. It's really suited for that. And so in this end, I think the end result is better. There are no real-time concerns here, so the fact of using Go is absolutely not a problem at all. And also, this means that you can apply the same framework for transparency on what is being produced because of the build reproducibility, the fact that you're just using Go. So I think it's a really good companionship for that, and it motivates this choice.
Thank you.
Yes? I knew you had a question. You always had questions.
Hello, Andrea.
Hello.
Nice to see you again. I'm curious about the secure non-volatile storage.
Yes.
You were mentioning temper sensors for voltage, temperature, and clock.
Yes.
And my question is, where is that? Is that the SoC or is that somewhere else? And also, are those detect or react sensors and hardware? Yeah.
So the cryptographic acceleration module from NXP provides 3 or 4 different sensors for glitching, voltage, temperature, and there's an external one that we don't use. We activate those, and as soon as they're tripped, they will set the device to a non-secure state, which means that if you try to derive keys, it will just give you a default key and it will not work. And you can also act on that trigger because it raises an interrupt and you can shut down. So that's how they work. We're not having external sensors like a point-of-sale device would have because you want to open. But if you try to glitch the device or to drop the temperature dramatically, they will kick in.
Okay, so the sensors are in the NXP die,
yes,
and
yes.
And they in hardware disallow access to the
yes.
key
It's
material.
called, I think they call it dry ice technology. So they have internal voltage sensor and temperature sensor.
Thank you.
Great. Okay. Thanks. Al?
Thank you.
Yeah. Bare metal go.
Okay, so we've gone very high, and then we've gone very, very, very low. And now I'm going to try to wendle my way in between the two. These chaps have spoken a bunch about what I was going to talk about, so we'll see how it works out. But yes, hopefully I can tell you about the firmware transparency because I'm quite excited about all of that. So as has been mentioned, everything is 100% open source. You've got the links to the repos there. There's the Apex repo listed at the bottom where you'll find all the tooling that we've spoken about. You'll find the documentation, witness IDs, configs, and all the rest of it. I think the only thing that we haven't open sourced are the secret keys. Here's the factory floor on my floor as we were building the devices. As Andrea said, everything's 100% open source. There's no U-boot, there's no Linux kernel, there's no glibc, there's no OpenSSL. Everything is 100% memory-safe language, all the way down to the mask ROM. Sadly, I couldn't change that yet, but maybe in the future. So we have our firmware repos. We need to turn them into firmware that can run on the device. So we have robots in our build pipeline doing that because we don't want any sticky human fingers anywhere near that. We have 2 pipelines. One's for our set of CI devices that triggers every time we merge a commit into main. And then we have a prod pipeline as well that happens when we tag a release on the repos. So these pipelines check out the code at the corresponding commit, do the build, do the tests, all the rest of it, and then they log the existence of this firmware into the firmware transparency logs that we run. So if we look a little bit at that, this is what we actually log. In terms of the claimant model, this is our claim statement. There's not a hell of a lot of stuff in there, and we can sort of walk through it. So there are 2 claims that are embodied in here. One of them is that this is like a release of version 0.2.1 of the applet, and the claim is that that semver version corresponds to the git tag, the git hash that's in there. So git tags are mutable, which sucks. And so in order to stop ourselves from being bad people, this basically binds us to have that relationship forever. And the second claim is that if you take all of the stuff that's highlighted in orange, so we know that it's a trusted applet, so we're going to check out the applet repo at that particular git hash. We know that we've used Tamago version, whatever it is in here, 1.22.4. and if we mix in a bunch of the stuff in the middle that I'll talk about a bit later on, then when you crank the handle, the firmware image that you get out the other end is going to have the base64 encoded SHA-256 that's there in yellow. We know that because Go reproducibility. And since this is a claim, the green line at the bottom is our signature, sort of staking our reputation on this claim being true. So just to go back, the big chunk in the middle that's sort of contained in the EMS section, this is really what's different between CI devices and production devices. So, firmware is all the same. This is really just where are my firmware transparency logs, what are the keys that I can use to authenticate stuff coming out of them, that sort of thing. So, we have our claims. Are they true? Am I making them up? Hopefully they're true, because otherwise there's quite a lot of egg to have on my face standing up at the front here. We do verify this claim as part of our build pipeline. We put the things into the log just because, let's be safe. But transparency, so don't take my word for it or our word for it. You should check for yourself. So there's a link there to a command called verify build, which Andrea hinted at earlier on. Or maybe Martin did, I can't remember now. But what this is going to do is it's going to go and look at the firmware transparency log. For every entry in the log, it's going to download that manifest that we looked at earlier on, and it's going to try to falsify that build reproducibility claim. So it's going to check out the repo at the right tag, and it's going to download the right version of Tamago, and it's going to set all the mvars, and it's going to do the rebuild. And if it ends up with a hash that doesn't match the one that's in the claim, then we get the big red X that's in the middle there, and it will also squirrel away all the evidence from its build so that someone can look into it. On the other hand, if it does do what we said it should do, you get the nice reassuring green tick and everything continues. And so you folks can go and run this command, and I would be super happy if you did, because this is what transparency is about. This is you all holding us to account. So please do that. Right, so we've got firmware. We have claims about it. It's built. Claims appear to hold up. And so we need to provision devices, as I mentioned earlier on in response to a question. So we take one of these blank devices and we want to turn it into an armored witness. So the tool that we use to do that is creatively called Provision. It's also open source, so you can go and have a look at how it works. So you can tell we're not doing anything too crazy. You basically plug in one of these devices, and then you tell it whether you want it to create a CI device or a production device, and that's just going to make it know which firmware transparency logs to go to, which keys to use. Then it's going to scrabble through that firmware transparency log and find the latest version of all the 4 different types of firmware that we have for the device, download them, do inclusion-proof checking, signature verification, all of that good stuff. And then it's going to put the device into recovery mode. Andrea mentioned that earlier on, which basically turns it into a USB mass storage device that exposes all of its flash to the host. And so then we squirt the firmware onto the flash in known locations. And we also store on there what Fillipo likes to call spicy signatures. So we've got our inclusion proof, which shows that the firmware manifest that is there as well is included under the checkpoint that's included. And that will become important later on. Device then boots, and if it boots successfully, then we do the secure boot fusing that Andrea was talking about earlier. Now, I know what you're thinking. This is all well and good, but what if Al just puts dodgy firmware on these devices at the factory with backdoors in, and then sends them out to the custodians? So I guess firstly, I'm disappointed that you would think that about me. It's not very nice. It's far more likely that Martin would do that sort of thing. But it is a good observation, and so I thank you for having it, because it leads nicely onto the next slide. So one of the things that we did when we sent the devices out to the various custodians, we also sent them a sort of little welcome pack, which did not include gummy bears because of export restrictions. But it did have a link to a little manual which sort of describes a bit about the device and all the rest of it and your responsibilities as a custodian. And one of them is to run another open source command, which is called verify, which does probably what you think it does. So it will, again, reset the armored witness into this recovery mode. which exposes the flash as USB mass storage. And then this verify command is going to go in there, look around at the flash. The bootloader has to be in a particular place because mask ROM. And so from there, you can sort of follow the trail to figure out where the other firmwares are going to be. It pulls the firmwares off. It pulls out the spicy signature proof bundles, redoes that sort of discoverability verification, does the hashing, inclusion proof, and everything else. If it's all good, as it should be, you get green tick marks. Oh, the other thing that it does actually that's very important is that once it's done this sort of offline inclusion proof verification and hash verification, it also then goes and talks to the logs to make sure that the checkpoints that were on device are consistent with its view of the actual logs. So I can't have done anything dodgy like having a split view of our firmware transparency logs. Right. So we've got a device, we've got firmware on it, firmware has been verified, so Al couldn't have done anything naughty. Andrea sort of basically stole my slide, so this is the boot. It does some things, he told you why it does the things. Those offline proof bundles are used when we do authentication by the bootloader of the secure OS and by the authentication of the trusted applet from the OS as well. What else can I tell you about this here that he didn't say? I think he probably told you everything. I've got one thing left. So when we do updates, or when the applet rather requests an update to the operating system, the only things that can be updated are the operating system and the applet. We cannot OTA update the bootloader because mainly the bootloader is not sort of covered by firmware transparency because the mask ROM doesn't do that. And so we decided we're going to leave that one alone. And yes, and when the update does happen, we use like an A/B partition scheme. So if it goes terribly wrong, the power goes out, all that's going to happen is the device is going to reboot back into the current version of the firmware. So yeah, and well, the last piece of my puzzle was given away by Andrea as well. So we do key derivation on device. So we never get to see any of the private keys. All we can do is ask the provisioned devices to please tell us what their public keys are, and then we put them up in the Git repo so that you all can see them. Why did we do all this stuff? Well, it seemed like fun at the time, but also, in essence, all of this makes it very hard for us or anybody else to covertly tamper with these devices, which is why we're okay sort of staking our reputation on these devices. Custodians at any point can run that verify tool, not only when they first get the device, but they can do it every day after an update, every Tuesday, whatever it is they want to do. Because of that, they get to see the manifest that's on device, and they know that it's sort of that is tied to the code because we have you all holding us to account with the code that's in the logs, which means that they can go and look at the repos, and because it's Go, they get to know the totality of the code that's running on the device. So if you have time, go in and look at it. Right? Anything looks fishy or suspicious, come and call us out. Write to the paper, whatever it is you want to do. We can't ship devices with dodgy firmware on because of the verify tool. We can't do a dodgy update and try to send out bad code. Well, actually we can, but it would be really bad news because it would be quite obvious. It will be in the logs, everyone will see it, and then we'll get fired. Anybody with physical access to the device, I mean, we've tried to choose mostly responsible and nice people, but some devices go missing. Ask me about that later on. But anybody with physical access to the devices can't boot inauthentic firmware, so our security properties hold. You can't mess with it. You can't reach in while it's booted and fiddle with RAM because it's encrypted. You can't tamper with it too much because it gets upset and shouts at you. So does this mean that these devices are impenetrable and uncrackable? No, of course not. We're a little team and we did the best that we could. But it does mean that in order to have much chance of disrupting this thing, you'll probably have to get your hands on at least half of the devices. And that's one of the reasons that they're spread all around the world. And I'm not going to tell you who's got them or where they are. But it helps to sort of reinforce that. So that's all that I have. Any questions? Okay, sure.
Hi there, Al. Is there a gentle introduction to how the witness selection happens, or how or if that can be changed by an attacker?
I'm not sure I follow.
So what I'm not understanding from the picture is if there's this universe of witnessers and there multiple witnesses sign the proofs, how is it possible to bias the selection of the witnesses in a compromising way?
Right. Okay. So so the witness identities are up on GitHub in a JSON file, and so as a log operator, if you're using the Bastion, you would say, well, I'm going to go and ask via the Bastion for co-signatures from all of the witnesses that are in this list, and then once you get back sufficient to have majority or whatever, then you'll continue on your way. So I guess the attack that you're describing would probably require me to subvert, or someone to subvert you, so that you go and ask for something else from the Bastion, or GitHub to maintain a split view.
Or go after a smaller subset of the witnesses in the list, I guess.
Yeah, I mean, this comes down to sort of the policy on I guess the log side and the client side as to how many signatures you want to see. Probably you want majority, so that you have to go after at least half plus one.
Thank you.
Yeah.
Quick one. So you had considered adding something like attestation reports, so that when the witness connects to the Bastion, it presents its report in the TLS, and so that you can verify it.
Yeah, so we can't, with the hardware that we've got, we can't really do that in the same sort of rich way that you'd have from SEV or whatever else. It's like, it might be an option for the future.
To follow up the question of Thibault, do you need to expand your current fleet of devices around the world, or is it sufficient at a particular scale?
And if so. So where we are at the minute, I think we're good. So there are, as I said, 14.5 devices. Ask me why later on. That's enough for us to start experimenting and seeing what availability is like, because these are basically devices, in people's homes and whatnot. So you're not expecting sort of 17 nines out of them. So we can get some sort of idea about what availability will be like. If we need more, we can up that number. If it's too many signatures to have sort of majority quorum, we can bring that number down. It will evolve over time, but I'll keep you in mind. Thank you.
On that note, I'm going to hold for questions so we can keep going. But yeah, please hit up Al with any more questions. Yeah. Right. Thank you very much, Al. Okay. Yeah. Our next speaker is Fillipo Valsorda, and looks like it's time to talk about monitoring.
Excellent. So what I love about Al's talk is that he presents an end-to-end story for not just how they're logging things, but also for how monitoring works, what is it that they're monitoring, what are the claims that are in the log, how the claims keep people secure. And I want to take a bit of time to talk about that. So I'm Fillipo, worked on Sunlight, worked on the Go Checksum database. I think most people in this room are tired of this introduction slide with that Zword Gophers. But if you want stickers of the Zword Gophers, I have some. Anyway, it feels like a lot of the transparency ecosystem early on was, well, we figured out a bunch of good ways to make logs. So that leads to transparent systems, right? You just log some stuff and then you draw the rest of the fucking owl, and that's how you get a transparent system. There were two, I think the first major missing piece early on was split view protection. So you now have a log. How do you know that it's the same log that everybody else is looking at? And that one we know how to solve now with witnessing. The two main solutions to that are witnessing and gossiping. You've heard a lot about witnessing today and not as much about gossip, because witness is something that you can apply before you accept a proof of something. So you can then alter the system based on the thing you are trusting, while gossip is something you do after. If you altered the system based on something that you plan to verify with gossiping, you're in trouble. Because now the system can be altered not to do gossiping. And then you don't have an owl, you have two circles. Right, so that one, I think we have a good plan, and if anybody wants to talk about running witnesses and taking on the commitment or the organizational commitment to keep one running, because it's kind of unpleasant to put a witness in the trust policy of clients and then ship that to whatever clients and then find out that it got turned off 3 months later. But if you're in for running a witness in the long term, we should talk about, we can help. And it's a very, very easy thing. If you're scared of, oh no, I heard how hard running a CT log is, I'm not up for that, way easier, because case in point, witness. So next issue in building secure systems is that really logging is what Alice said in his keynote. Logging is worthless and by itself, and and I really like the parallel that Alex Gaynor does here. Here he's talking about signatures. He's not talking about logging. He's not talking about spicy signatures. But what he's saying is that just like backups are worthless, what matter are restores. Signatures are worthless. What matters are verifications. So if you don't have a good story for how you're going to restore a backup, you don't have anything. If you don't have a story for how you're going to verify a signature, you don't have anything. If you don't have a story for how you're going to, well, fail closed on a proof and then monitor the entries in a log, you don't have a transparent system. And I'm sorry for being the little more downer talk of the session, but this is more about, I think that we built a lot of fantastic tooling to draw a full owl, and I want to see more systems like the one Al just described that go end-to-end into a full system. So let's talk about monitoring, both having a story for how monitoring is going to work and the tooling to do it. So to do that, I want to establish a bit of language, and sorry. Well, so this has been hotly debated over time, and I've gone back and forth a bit, but I think it's useful to define two different terms for the verification of the log that you can do at point in time and globally. So the sort of thing that as long as somebody does it, at some point, misbehavior will be caught. For this, I like to say that any grad student anywhere downloading the log and running the check is sufficient to keep the entire system secure. I call that auditing, because it's a point-in-time audit of the entire system. And that one doesn't need to even know who the users of the log are. They need to know what the ecosystem is. But yeah, anything that's point in time and asynchronous, I like to call auditing. While monitoring is the thing that needs to happen synchronously and while entries are generated, and that usually needs to speak to users because it might not be self-evident what's a thing that's not supposed to be in the log. So auditing is about things that are just wrong. Like there's a duplicate entry in the log. The log should not have duplicates. It has a duplicate. Bad log. Let's have a conversation. No need to talk to anybody about it, except, well, anybody to ask if it's correct or not. Monitoring instead is, well, is this a valid firmware? Was this built correctly, or is this? It's much squishier in a sense. Now, to build the system end-to-end, you need to have an idea of what both of those roles will want to be checking. And there needs to be a reasonable way and tooling for those roles to be implemented. So this really goes back to what I think defines a transparency log. So what are the entries? Who can add entries to the log? And who monitors entries? The two relevant ones to what I'm talking about are the first and the last. Why the first? Because the entries need to have in it enough to let the monitor only look at the ones that they care about. If I have just a log of hashes, just an endless log of hashes, and I don't know which ones are builds of armored witnesses and which ones are instead hashes of, I don't know, AGE releases, and I can't tell them apart, I can't monitor them. I can't. So I need in clear text in the entries enough to take apart the things that I'm monitoring and action them from a monitoring point of view. And for the auditing side instead, I need to know what is the log committing to. Is there a uniqueness guarantee? Is there a guarantee that some metadata will always be fresh? Is there a guarantee that the timestamp only goes up? That all of those need to be documented in the system and committed to in advance, so that then your auditors and monitors can actually check them. I'm going to make negative examples. So in order to make negative examples, I'll pick systems that I was involved in, so I'm not criticizing anybody else's system. This is the Go Checksum database. Its deployment was a success. 100% of Go modules were protected by the checksum database overnight. There is no opt-out. It just, well, there is an opt-out, but there is no opt-in. It just works. And this is the thing that the Go CLI fetches every time it downloads a Go module. For example, if you're fetching this version of my Edwards 519 library, you're going to ask endpoint that will give you, this is a checkpoint, the name of the tree, the size of the tree, the hash of the Merkle tree head, the signature from the log. Imagine there are witness co-signatures here. And these are the actual hashes of the library. And this is the index in the log where you can find it. There isn't inclusion proof because this predates spicy signatures. If I designed it today, it would also just have a inclusion proof. Instead, you fetch it in parallel. Ignore that part. Now, what's auditing? Auditing is clear. Auditing for the Go Checksum database is you take the entire log and you make sure that there are no duplicates. There must be exactly one hash for Fillipo.io/Edwards25519 version 1.1.0. And every entry needs to have the hashes of the Go mod and the hash of the whole library. Auditing is fine. Split view attacks, again, imagine there are witness co-signatures. That's how we solve that. But what about monitoring? That part is something that we hadn't built ourselves, partially because you kind of can't expect the log operators to do the monitoring. If you delegate monitoring to the log operator, you kind of went in a circle. So thankfully, eventually, somebody built it, and they built Gopher Watch. Gopher Watch is just a website that monitors the Go Checksum database, and you type your email address, and you type what packages what modules you care about. So I went in there and typed my email address, and I typed Fillipo.io/... Anything like that, send me an email. So now I get an email every time Google puts a new entry in the Go Checksum database for a Go module. Now that's end-to-end story. Now I can, I actually trust that anytime something is published, I'll know about it. How do I know the entry is the correct one, though? That one was a tooling gap. So now we have a proposal to add a command line option to a command line subcommand to the Go CLI, so that you can do Go mod verify. And what it will do is take all the tags you have locally on the laptop where presumably you even developed the library, and will go to the checksum database, get the hashes, compare them. Now it will guarantee that anything I developed on my laptop, and if my laptop is compromised, well, that's out of scope. That is not the attacker we're defending against. Anything that's on my laptop is exactly what's in the Go Checksum database. Since it's in the Go Checksum database, is what every one of you is using when you fetch that library. We close the whole loop. We know how the thing is correct in the log. We know what the auditors are checking for in the log. And now we have a monitor that will notify me. Even better if there were multiple monitors. Ideally, there would be that Gopher Watch that's free, but also I would be able to pay my supply chain security provider to just automatically keep an eye on anything of the dependencies I use, or send me SMS, which are expensive and Gopher Watch want to do, etc., etc. The more monitors, the better. Great. So this is an example of two gaps that where stopping that system from being a complete end-to-end transparency system. Let's look at another one. So I developed this library, this command line tool and library. It's called Age. If you want stickers, I have stickers. I like stickers. And it was kind of embarrassing that there was no T-logging for Age because, I set up Sigsum, and you heard about Sigsum, so you know that it's a way to ensure that any signature generated with a certain key is logged. I made 2 keys. One of them is printed out on a piece of paper in a safe. The other one is on a hardware token, so that I can only it cannot be extracted and cloned as a extra layer of security. And then now anytime I make a Age release, I publish that to Sigsum. Sigsum has monitoring tooling, so you can get a feed of every time I sign a new Age release. Does that do you any good, though? I didn't write the scripts that let you then, I didn't even say what I'm committing to. And I'm calling myself out on what's missing from my reading here. Just by reading this, you don't know what you're expected to find signed by that key. What's missing here is me saying, okay, I promise that anything I sign, you will find as a GitHub release asset. And not only that, I promise that GitHub release assets were built by the GitHub action that was active at the time, and if you look at it, you'll see that it's a reproducible process. Even better, here is a bash script that you can run on any Linux system to rebuild the same binaries. Which, by the way, is a really tricky thing to promise in the future, because I will want to change the build process at some point. And when I do, now it will not build the same thing for the older releases, but it needs to do that to keep matching. But all of that can be fixed with tooling because, for example, I can put in the verifying script something that checks, is this before version 1.7.3? Then I need to use this other build process to compare it. So here instead, what's missing is tooling. I think it's important to tell these end-to-end stories, and how exactly you build an end-to-end story changes based on your ecosystem. I have a few more examples here. Binary transparency is similar to this. You need to commit to what exactly you're logging. You need to provide some way to get confidence in the thing you're logging. You could say, well, the binary is out there, so you could always reverse engineer it. You know, it's better than nothing, but you get a lot more out of the system if you can say, well, you can always reproduce it from a Git tag that's in Git. If instead your package registry, you can use it to hold yourself accountable for the decisions you make, also based on what accounts are doing. And in general, what I think this is about is that until 6 months ago, a year ago, transparency was something that was mostly talked about amongst people that already had an idea, a vision of what they wanted to secure with transparency. We would get on calls with Al or on call with Rasmus, with Niels, and be like, yes, Frederick. And we would always be like, yes, yes, we know what we're building. We know where we're going. Here are cool ways to build pieces of that story. I think it's now being successful enough that it's starting to escape that bubble. We're starting to present it to ecosystems that don't have an intuition for what's the end-to-end thing we want to achieve. And if we offer them a way to log a thing, they will log a thing. And then they will have 2 circles and not an owl. I think it's important we give them the tools and the stories and the guidance to build end-to-end systems that have realistic auditing and realistic monitoring stories. Thank you. Fantastic.
Have you thought enough about sort of the monitoring story, right? Because it seems like it becomes a very critical component for developers to, detect misuse, right? sort of we start shifting the trust to say only having to compromise the monitor in order for me to say hide something, right? You did mention that it's great to have multiple monitors and stuff, but it seems like there's a lot of dimensions there in terms of diversity for implementations, etc. Yeah, have you thought about this and what sort of, I guess, framework we can use there?
Yeah, no, it does depend a lot on your ecosystem, right? We're chatting with, well, I will not out them. We're chatting with somebody who runs a CA shortly ago, and what they said was, well, we can always just pipe it into our audit log process already. We already have a sync for that kind of thing, and that's a powerful answer to your specific ecosystem. Some ecosystems can even say, you know what, we're just going to do it on the client. Key transparency. Key transparency is basically entirely based on the predicate that the client itself is the only one that could have generated a key. So any new key for that needs to be aware, the client needs to be aware of it, and then it adds a lot of complexity to allow efficient monitoring. Remember that here for key logs, mostly monitoring means you are going through the entire log, and hopefully the log tells you enough to take out the ones you care about and then email about those, but you're just scanning the whole thing. Key transparency does a lot more stuff to be able to instead look at the entire history on the client, which is limited though. It means that if you uninstall WhatsApp, there is nothing that will tell you if somebody is adding keys to your phone number. So there are a lot of trade-offs, and it's the part that I'm worried we can't make as much of a cookie cutter solution for, which is why this is more of a squishy talk in a way. But yes, for things like Go, I like to imagine settings where there are different monitors and where you access monitoring through different things. Maybe you pay some company to run a monitor for you, but you also sign up for Gopher Watch, and those are different enough relationships that doesn't make sense for them to collude, right? Also, you can always add monitors after. It's different from witnessing, where you fix the policy, and that's the policy, and that checkpoint is witnessed by that. Monitoring, you can go like, well, that one shut down. Let me just Google for another one, sign up for that one.
Okay, there we go. Hey, when you mentioned Gopher Watch, that monitor, that reminded me of something I haven't thought about for a long time, which is KT or prefix-based or prefix-ordered logs as a tool for auditors. And my question is, what do you think the future holds when it comes to, let's say, you're auditing a log, such as the Go Checksum database, which has a policy of unique releases or unique strings per release, and then effectively you have a need to build up this database of what have we audited, what have we not audited, and you can even see some new type of well, it's not really co-signing witness anymore. It's a different policy. It's not checking consistency. It's more about auditing reproducibility or whatever, and you can have MOVAN there too. But the point being that using authenticated search prefix-based log to help you build up a history of what have we audited and not. And so my question is, what do you think? Prefix ordered logs and auditing, do they help?
Yeah, I have two answers to this. One is that an auditor that wants to offer that service to multiple ecosystems that have these uniqueness guarantees can build that tooling and then use it to offer a service and to prove that they're offering the service correctly. And I would love to see that. The other is that I also want to think more about when that use case is common, which it seems to be, and whether we can start thinking about standardizing on a design like that for transparent maps, something that's simpler than the whole AKD construction of key transparency, which is delightful, but also a lot of moving parts compared to what we're building here. So if there is a simpler system, but that one is much more in the drawing board, while this was about, okay, we've got the thing, let's get it into the hands of users. I think those are different timelines, right? Thank you.
Any more questions?
Hey, it's on. Great talk. So transparency is successful in escaping the bubble. Does that mean that we have to start talking about the business value of transparency to people, and what does that pitch look like?
Yes. So part of this talk, the point is we need to be able to articulate that. We need to be able to articulate what transparency does for a broader system that you want to bolt it on top. I'm actually fairly optimistic about transparency in this age, because the whole reason I work on transparency is that I think it addresses something that's hit a wall otherwise. Centralization is so sweet. It just makes everything work. Come on. Yes. But at the same time, there is more and more techlash, more and more lack of trust in the centralized operators. So I think that there is an appetite for a tool shaped like you can centralize the thing, but you can make meaningful statements as to why that will be done correctly and be transparent about it. That's how I've always pitched it, and I've heard it pitched similarly at other companies that as soon as started having it as a tool in the bag, started reaching for it a lot more. So yeah, the first way I find to pitch it is you want to centralize, because that's what lets you ship the product. That's what lets you do the thing that works best, and most users care about that. But then you have a bunch of users and the regulators that care about not giving you all that trust that you need to ship that user experience. How do you square that circle? Well, that's the best way I found so far to articulate that. But part of this talk is, the point of this talk is, I would like people to think about that, because we used to talk it amongst ourselves to figure out the best way to build the thing. Now I also think we need to talk about how to get the thing to appeal to others. And on the note of business, I think somebody should take auditing and monitoring and build a business out of it. I would be doing that if I hadn't literally started a business this summer. So not another one. But somebody should be just going to the Meta and to everybody who has one of these ecosystems. Google, probably, not Google, the Go team. When I was on the Go team, would have been interested in talking to somebody who could deliver us, you can't be the monitor, but we can be the monitor, and then you can tell your users, well, this company is not Google, and you can use them for monitoring, or you can build your own. Somebody should go and build that. And yeah, talk to me if you want to build it. I don't want to take a piece of it. I just want to help. I want that to exist.
I think on that note, that's a good time for a break and carry on the discussion. We're going to have a short break. Maybe we'll keep it to 10 minutes so we can get back on track. And then we'll come back for the lightning talks after that. But thank you very much. Let's have one more round of applause. We're going to get going with the lightning talks, so please take your seats. We have 5 awesome lightning talk speakers. They'll each be doing 10-minute talks. We will have time for maybe 1 question as we switch over, but I do encourage folks to follow up with their questions after the talks and in the discussion spaces tomorrow. And yeah, really grateful to all our speakers who stepped forward. It's just a nice way to get a bit of a fast and furious touch on a lot of different topics and hear from some different people who are bringing new and interesting viewpoints. And with that, I would love to kick over for the first lightning talk to Lena. So please, everyone, give a warm round of... Oh, hang on. 1 second. Roger, I need you to... sit down. Okay, I would like to welcome Lena to speak to us about SCT auditing. Please give her a round of applause.
Thanks. Yeah, we already talked about how we need to perform audits for our transparency system to work. Just most of you will know about SCTs, but just so we're all on the same page, we use them as promises that eventually a certificate will be logged. Give it to the user as a part of the certificate, and then if it's not included in the log, especially in the certificate transparency ecosystem, we have like this kind of niche attack where you need to control at least 2 CT logs and a CA to perform an attack. The problem is we don't have the many logs right now, but in the future we may have more logs. So kind of like the success of the ecosystem means that we will need to audit a lot more. So that's nice, but the problem with auditing is that we leak our browsing history and we would like to audit privately. So what's currently being done, there's a bit of auditing by browsers. So Chrome does some auditing depending on your safe browsing settings, sometimes also some extras. Safari uses the Safe Browsing API and also does some proxying, and if you use another browser, most likely you're not auditing your SCTs. So why don't people like proxying? On one hand, because there's some possibility for traffic analysis, which is why Chrome does some sampling as well. And also we assume that the auditor and the log don't collude, and that's not what is practical. So we wanted to look for alternatives, and there is a really nice SOC that discusses all of the alternatives that have kind of been proposed. It has a good overview, so I'm not going to cover that all today. I do want to talk about some things that are made possible by recent developments. One of them is private information retrieval, or PIR. We like it because it's the natural solution. You have a private database lookup. And that's kind of what we would like to do. The SOC came out in 2022, and there's a number of new proposals since then, and PIR is a really active research topic, and the protocols get better and better. What's also really nice is that we now have static CT, and then we have sequencing numbers, and that enables us to look up a hash of the certificate by the sequence number. And previously we would have had like the hash of the certificate, and then we look up something else, and that's not that great. So the ecosystem is actually moving into a direction where PIR becomes possible by deploying static CT. And the original motivation for all of that is that there's fewer audits if we use something like slow embedding in parallel as well. Why would you use a slow embedding certificate instead of what we have right now? The reason is quantum computers. So if we want to exchange our nice elliptic curve signatures with something lattice-based, our certificates are suddenly going to be much larger. And the idea is to use Merkle-style certificates. There's a number of proposals. I'm not going to cover them. I think there's another talk about them sometime. But basically, you add a cryptographic proof of inclusion and then distribute the tree heads over time. And they're great, they're small, they're fast, they're secure against quantum computers. But you can't get a new certificate immediately after it was... so you need to wait until the tree head was distributed. And we wanted to find out, well, when do you actually need a certificate immediately? So that's now a bit of the experimental part of the talk. If you find something that we missed, please let us know. But we found 3 scenarios where you want the certificate immediately. The first one is when you register a new domain and want to use it immediately. Then you want a certificate right now. Then if you have misconfigured your automatic renewal or don't do automatic renewals, it could be that you find out that you don't have a certificate via an error. You also want to fix it right away and not wait until some Merkle tree heads have propagated. And the third reason we found was if you switch provider without planning, so for example, because you're under attack. And we looked at public CA logs to try and get a loose, very, very loose upper bound for these scenarios, and found out that actually between like 1 in 1,000 to 1 in 10,000 domains would need fast issuance, so something that is not slow embedding. To give a concrete number, that's like just under 1 million certificates at a given time, assuming it takes 3 days to propagate tree heads. And like 1 million is nice, and 1 million is also a good size for a database. So we kind of wrote a wish list as a next step on what we would like to have our peer scheme to have them. And the first one is pre-processing. We don't want to do any, but if we do some not per client, an example of that would be we're okay with pre-processing a database a bit cryptographically. We also don't want to recompute the entire database if we have an update, but maybe some updating mechanisms to take like, we thought 10 minutes, but in some discussions today was more like a second. So we're really happy to discuss that. We don't want to leak anything again, but if we do, right now Chrome uses a bit of differential privacy, and we want to be better than that. An example of that is for reusing public key material that we pre-distributed for a while. So then you can say, okay, this audit came from the same person, but it doesn't matter because you don't know what the query is anyways. Concerning timing, ideally we would like to be done with it immediately, but we may actually be able to batch it. Well, we thought 1 audit per day, but maybe that was a bit generous. But let's talk about batching, because it turns out that we are okay with having a sum of hashes if we have a private database lookup by sequencing numbers, because we can't compute collisions if we have a private lookup anyways. And all of the peer schemes that we have are lattice-based, so they support batching natively anyways. So let's look briefly at what the state-of-the-art of peer is. Maybe we missed something, sorry about that. But what we can have constant communication size, but then we need public parameters. We can reuse them, but the query is kind of like we have a computation trade-off here. And the 80 kilobytes are computationally relatively expensive. So we have a bit of a trade-off here, which is nice. If we don't want to have a state, we need something like hintless peer or Frodo peer. There we have 3 megabyte queries, but we don't have a state. It's dependent on database size, so if we actually want to do it for the entire ecosystem, it gets more expensive. Yeah. And it's super new. It's like from Crypto 2024, so we're not sure how it performs in practice so far. There's also like Spiral, where we have really large public parameters, so we'd need to reuse them for a while to amortize. But we have a 37 kilobyte query, which is for peer relatively small. Yeah, but the communication is also dependent on the AOS size, so also not that great if we want to use it for more than MTC. So yeah, to sum up, we currently don't audit very much. If we do, it's proxied. Static SCT is really nice because we now have sequence numbers. I think Trillian also, Tessera also has them, which is also nice. There's also a bunch of new peer protocols that also move in the direction of making lookups by peer more practical. And if we leverage something like slow embedding, we potentially can reduce the need for lookups by a really large factor. And also we would only need 1 peer call per audit. So we only need 1 response, which is nice. Something to keep in mind with the discussion though, if we only have a database with 1 million entries, each entry is 256 bits, generically downloading a list of valid certificate hashes is just 30 megabytes, and we don't need to perform any lattice cryptography. So yeah, we should be definitely better than that. Yeah, that's it. Thank you.
Thank you. Roger, can we get you come set up, and we will take a question or two.
Hi. How did you figure out the 1 million number for the certificates that require like immediate access? I'll use access as a term, because personally to me that feels extremely low for that use case.
There's the easy case, which is new domains, by just looking at new issuance. I think Let's Encrypt even runs Let's Encrypt has a statistic for how many certificates they issue, and then you just subtract it, and then you kind of get the trend from it. We do have logs at Cloudflare. That was quite helpful. For the moving part, we looked at domain renewal patterns. It's a really loose upper bound, but basically we said most people seem to renew the certificates 14, 30, or 90 days before they expire. And then we were, okay, if you move CA and you're roughly outside that pattern, so we also gave it a bit of a grace period, then we assume it was unplanned, which isn't the case. Like some people also, like obviously we're going to have a really high false positive rate, but we're fine with high false positive rates because false positives don't matter. If the system performs even better deployed, that's nice. And for expiries, it's also easy to measure. You look at the CT logs and see, hey, did you have a gap in your certificate? That's again false positives because we don't have all of the certificates, so that there is a possibility that we said, oh, your domain expired, but it didn't.
Okay, great. Up next with CT log ingestion, please welcome Roger.
Hello, everyone. I'm Roger from the Google Trust Fabric team. Today, I'm going to talk about CT logs injections from RFC 6962 to static CT API. So first of all, we will quickly go through what is CT log injections. Then we will start our journey from RFC 6962 to static CT API. And then we will have some challenges and key takeaways. So what is CT logs injections? So it is the process to ingest the certificates from multiple CT logs. But it's not just about getting all the certificates. It's very important to verify them with inclusion proof and consistency proof because you always want to store verified data. So let's start with the ingestion journey from RFC 6962 to static CP API. And we are going to start with the Google Argon 2024 CT logs. Okay, first of all, we can call the get_STH endpoint to get the tree size. And then we will call the get_entries endpoint to get all the entries according to the tree size. Let's see what happened. There is a lot of data, so we got to find out the length. So we are going to get 32 entries. So it's 32. So at most, so we can get at most 32 entries per request. So next, we're going to use the SCT scan from CTGo repository to get the QPS from our Argon 2024 logs. With 50 parallel fetches, the QPS looks actually pretty good, but it's going down now. We are fetching a lot of certificates, so eventually it will get to 0. Running out of coder, it's going to take a minute to get to 0, so we are going to skip this. Perhaps some other people will try to do this with multiple IPs to get through it, to make it faster. And that's what will happen. We are going to receive the page if there are too many people trying to download the certificates at the same time. So on top of our journey, we can also find others' journey in the certificate transparency Google groups. There are questions from time to time asking about how they can effectively download all the CT logs and parse them. So let's try to fetch the entries from our static CT API logs. It's really quick, as you can see. So the number is around like 90,000 QPS for this log. So let's go into the challenges. Are they really challenging? So we are building on top of the existing pipeline instead of a fresh start. And the pipeline is actually like building the Lego blocks. We have we have to get the assigned tree head and then verify the consistency proof and then get the entries for the RF26962. Now we're going to add the static CT API on top of it. So the first challenge, but we can say is a difference. The first difference is the STH and the checkpoint. So on the left-hand side, that's the RFC6962 STH. And then this is the checkpoint from the static CT API. So actually, the tree size is the same. And then the root hash is also the same. So they are actually backward compatible. It's not too difficult. Another difference is how we verify the consistency proof. So in RFC6962, we would call this getSTH consistency endpoint, and then it will return an array of Merkle tree nodes. And then we can call the verify consistency to check whether it's valid or not. For the static CT API, the consistency proof moves from the server side to the client side. We got to get the positions of the tiles for those nodes, and then we get those tiles and then find out the nodes data. So we have the same data set to verify the consistency in static CT API. And the next difference is we got to fall back to full tiles when the parcel tile is gone. So the parcel tiles, they got a format like that with a .p/w, which is the width. So now we got a static CT API log and also got a monitor. This is the timeline. So each data tile contains 256 entries. So let's assume the log size grows by 50 every second. So we will start with 200. The log monitor would get the checkpoint of the size 200, and then the log grows to 250. And then the log monitor starts to validate the consistency proof. And then the log grows again. And then the log monitor would try to get entries from this parcel tiles. But it's a 404. This is because the parcel tile could be gone when the checkpoint goes over 256. And we have to fall back to the full tiles, which, this is the full tiles. It contains 256 entries, but you can get the first 200 entries because they are already proof that they are issued in the checkpoint. And there are another the final difference is the structure of the certificate entries. So I will highlight them. The X509 entries is empty in static CT API, and the certificate chained, they are now hashed instead of data when compared with RFC6962. But don't worry, you actually have the data to reconstruct them. So if you're building on top of the existing pipeline, make sure you convert the new format of each entry to the RFC6962 one. So here is the key takeaways. CT monitors should embrace the static CT API logs. So as you can see, there are differences, but not challenges. It's never too early to be ready. And Google is ready for these static CT API logs injections. So thanks, Josie, our next speaker, for the great work. And thank you all for listening.
Thanks. Can I ask Josie to come set up, and we will take questions for Roger. Any questions? If not, thank you very much, Roger. Let's have another round. And while we're setting up, I'll start giving you a sneak peek from tomorrow. So tomorrow we start at 9 again. It'll be similar to today. You will have to come and pick up a new badge. So on your way out, they'll ask for these back, and they'll give you a new one for tomorrow. We will also have breakfast up in this room, and talks will be starting at 9:30. So we have a half day worth of talks, and then in the afternoon we'll be splitting up into the discussion rooms, certificate transparency, binary transparency, and key transparency, and I'll share more details about that tomorrow. Okay, so our next lightning talk is about Deps.dev, and let's give a warm welcome to Josie.
Hello, yes. Hi, everyone. I'm Josie from the Deps.dev team at Google, and we are working with Roger's team, Trust Fabric, to manage the pipeline that ingests data from all the certificate transparency logs. So yeah, I worked with Roger to implement Sunlight or static CT support for Google's CT ingestion pipeline. I'm giving this talk to spark ideas on what Deps.dev can do with all this CT data that we have stored and indexed. And we definitely want to hear from you, so please feel free to grab me or anyone else from the Deps.dev team. Jesper's here, Eve is right there at the back. So yeah, feel free to grab any of us from Deps.dev after this session if you have your own use case for this data. So I mentioned that I'm on the Deps.dev team, and Deps.dev is working with Roger to house the CT data. But what is Deps.dev? So Deps.dev catalogs public data and metadata on supply chain artifacts, and in particular open source packages, with a focus on open source packages. We fetch, process, and then serve this data. Ultimately, Deps.dev helps you to understand, analyze, and make decisions about the open source dependencies that you use, are thinking about using, or might depend on without even knowing it. So here is a screenshot from the front page of our website. You can browse packages from NPM, Go, Maven, PyPI, NuGet, and Cargo. We track every package for each of these open source ecosystems. Before I get into it, just so we're on the same page, here we have a package that you've chosen to depend on, and it itself has dependencies, and some of those also have dependencies, and so on. So by trusting package A, you've implicitly taken on all of these other dependencies. So you might want to find out what's actually in them. You can search for a package on Deps.dev. In this case, I've searched for the npm package Express at version 4.16.4. This is the page that we show for that package version. And a few things I want to highlight. We show the security vulnerabilities known to affect this package version. We get the security vulnerability data from Deps.dev, and then we join that with our dependency data. So for Express 4.16.4, it has a couple of vulnerabilities, both in its package and its dependencies. These have, thankfully, all been fixed in the latest version of Express. We show the license of each package. In this case, we have the license of Express 4.16.4, which is the MIT license. And we also show dependency license. So for the dependencies of Express 4.16.4, most of them also have the MIT license, but a couple of them have the ISC or BSD license. So if you're using this package, you might want to check that those two licenses are also compatible with your project's policy. We show the number of dependencies and dependents of this package as well. We break that down by direct and indirect ones. The last thing I wanted to highlight is that we give the ability to visualize the dependencies of each package. So earlier I showed you a representation of a package and its dependencies, where in real packages it's often much more complicated than that. So this is what Deps.dev got when we resolved Express 4.16.4's dependencies. The colored dot in the middle is Express, and all of the other nodes are dependencies of Express. And because dependencies have dependencies, this is visualized as a graph. You can also filter this graph for specific things, like in this case, we have filtering for nodes with a security vulnerability. This data isn't just available on the website, Deps.dev, although it does make for good slides. It's also available on BigQuery through our BigQuery dataset and our API. Our API is completely free. So what we do at Deps.dev is we aggregate and analyze open source data and make it accessible and useful. We fetch this data from many different sources, process that data by abstracting away different ecosystem idiosyncrasies. We compute insights on them. We might join that data together, and then we finally publish it through the ways that I mentioned earlier. I've mentioned package data a bit so far, but we're also processing and serving vulnerability data. We've been ingesting Sigstore and Record data, and we're excited to be working with CT data too. As a team, we're new to the CT ecosystem, and we're not CT experts yet. Our expertise has been in ingesting and serving open source package data. So we want to hear from you about how we can make this CT data useful to you. What can Deps.dev do for the CT community? We're definitely not the only group looking at CT data. There's already lots of really good work happening in this space. And we're wanting to collaborate, support, and supplement what needs and requests do you have that aren't currently being met, or maybe what you want already exists, but it's helpful for you to have more than one project providing the same service. We're hoping to do something similar to what we've done with package metadata. The package managers themselves, like NPM, PyPI, and Maven themselves have data, and we process it to make it easier to hold and use. Similarly, in CT, the logs already have the data, and we're hoping to do the processing to make that data easier to hold and use. I've brainstorm some ideas in the next few slides, but they are by no means exhaustive. So yes, please come and talk to us if you have your own use case for this data. This is just to get the discussion started. Some ideas that we had for what Deps.dev could do for domain owners. Deps.dev could be another service that lists certificates per domain, maybe through our free API. This could be helpful at the point when registering a domain to check that the SSL certificate hasn't outlived the domain expiry, which might help to prevent bygone SSL attacks. It's also the data that domain owners would need to construct alerting for certificates, mainly to detect certificates issued without their knowledge. We could also implement some kind of outlier detection through time series analysis. So in other words, we figure out what normal activity looks like for this particular domain. Perhaps you use a specific domain registry, or you always renew your certificate 30 or 90 days before expiry. And once we figure out what normal activity looks like, we can figure out what abnormal activity looks like, and that might help to reduce noise on new certificate alerts. We could also provide phishing domain analysis. So for a given domain, tell me if there is a potential phishing domain for this domain, maybe through edit distance to start off, and then we can expand to more sophisticated methods. For log owners, we could provide statistics like uptime, which user agents trust each log, latest STH, that we observed. We could also provide statistics specific to capacity planning, like certificate throughput, how many certificates have been submitted to each log, but also how many certificates are unsubmitted to each log as well. So in other words, given a log, this is the number of certificates that were submitted to a different log in the time frame that the log has been up, but weren't submitted to this particular log. It would be good for the operator to prepare for that capacity, as running out of disk space can cause corrupted data. We could also provide statistics on progress towards static CT adoption. For example, how many certificates submitted in the last month, say, exist in a static CT log. For a user agent, we could provide statistics on log criticality. We provide the data that the user agent then combines with their data to figure out what percentage of HTTP connections would break if they were to distrust a specific log. So for many reasons, a user agent may need to just distrust a log before the expected date, and it's good to get an estimate of how many connections would break before enforcing that decision. For open source package ecosystems, we could use CT data to get insights into the URLs listed in the package metadata. So that could be a homepage or a documentation page. These are often unverified by the registries and are close to being free text fields. So we could check whether a valid certificate exists for that domain and whether that domain is expired. If it is expired, that could be a signal into whether the package is still being maintained. Deps.dev tracks a few million repos on GitHub, so we could do some interesting analysis by combining CT data with the code observed on GitHub. For example, we could detect when people are pinning certificates or pinning issuer keys. We have been working to make our other transparency data that we ingest recall available to academics, so we could do the same for CT data. And let us know, what can Deps.dev do for you? Are there any indexes on CT data that you would like, specific access patterns, use cases you would like solved? Letting us know tells us where to focus our efforts. Thank you.
Thank you. Can I get Dennis to come set up and we'll take questions.
Hello. Thanks for the great talk. I just had a question about the dependency stuff you mentioned about Deps.dev. So for a complex package, that could be a pretty deep tree. Is that all the levels of the tree is covered, or you stop at a point?
You are sitting next to Jesper, who coded the UI for that. Sometimes it gets a bit slow, but we do show all the dependencies. Yeah. Okay. Because you're right, some of them have, heaps and heaps of dependencies.
Another question I had was, is it linked to your analysis in the background with connected with some SBOM stuff for each of the package, or how do you extract that data?
Is that question how do we get the dependency data?
Yeah.
Okay, so we have implementations in Go of all the resolution tools like NPM, NuGet, pip, and so on. We have fast implementations of them in Go that are replicated bug for bug, and we run them every day, multiple times a day, I think. Yeah.
Thank you.
Thanks for your questions.
Great. Okay, thank you very much, Josie. Next lightning talk is intriguingly around CT and Katie, which I will let Dennis tell you more about. Please welcome Dennis.
Hi, everybody. So this is in some ways the perfect follow-up to the discussion from earlier, where people were asking, KT delivers some interesting things that CT or existing kind of flat transparency logs don't, but KT is also pretty heavyweight and achieves some properties that we maybe don't want in public logs. So as we've also heard from a lot of different people, when we look at the CT ecosystem, the big story, the big problem, the pain point really comes into some of the monitoring and the lack of end-to-end monitoring. At the end of the day, it's fantastic that we have this kind of strong audit story for CAs and for logs, but it really breaks down when we get to the end user. And website owners can't efficiently audit their what's been issued for their domain. And it fundamentally boils down to trusting crt.sh at the moment. And obviously, Sector.go are great folks, but you can't actually verify whether they're doing a good job of monitoring your domain for you without going and scraping all those different logs yourself. A second pain point that we have is that operating a log is fundamentally an expensive proposition. Every log has to serve a full copy to every monitor, so adding more monitors makes the log's life much more expensive. Similarly, for the monitor, adding a new log means you have to monitor that as well, so adding a new log makes the monitor's life much more expensive, and all of this scales with the fire hose that is the web PKI and the certificates it's issuing. So together, I think this makes a really challenging position for delivering end-to-end transparency for the web PKI, where we can actually get it into the hands of website owners. Now, meanwhile, in the key transparency world, they've gone with quite a different model. And depending on the exact solution that's in use, either we have users directly talking to a key transparency system, and they're receiving short succinct proofs about their keys, the keys that they're interested in, which is backed by some kind of auditor statement, which they maybe consume indirectly through a signature. Or there's no auditor and the users are gossiping between themselves and using that to establish whether they have this kind of nice end-to-end transparency property about the keys that are of interest to them. Personally, a few years ago, I would have said I was a bit of a skeptic on KT. It seemed pretty cool, it seemed pretty fancy, but it seemed to me very academic and complex and maybe hard to realize in the real world. But we've seen in the last couple of years that Meta and iMessage, they've both shipped key transparency solutions to end users that are working at a pretty phenomenal scale. And I'm sure they're not perfect, and I'm sure there's many pain points, but it's compelling to me that KT systems are deployable and potentially offer different trade-offs. So this kind of leads to the direct question: what can you borrow from key transparency systems to leverage in like a future CT system? And I think, as Fillipo alluded to, distant future. This is not like next year, this is maybe not even the next 5 years, but maybe there's an opportunity here for something new. And a key observation is that the key transparency folks are trying to deliver a really strong privacy property. If you're using KT, you're storing user identifiers fundamentally, and you don't want to leak information about how many users you have. That's commercially sensitive as a business. And your users don't want to leak kind of their update history and when they're online and when they're doing things. So KT systems work really hard to deliver this privacy property, and we functionally don't need that in the world of certificate transparency, where everything's public, or in the software transparency world, where again, our artifacts are typically public. So in the rest of this talk, we're going to sketch some of that owl, and we're not going to draw the whole owl, but I think we're going to get pretty close, and I hope it's going to be compelling. So the first kind of thing that we're going to need, the first primitive, is an efficient, verifiable map. And the one that has been increasingly used in the key transparency world are Merkle-Patricia trees. And if you've not seen these before, you're not going to learn them in the next 30 seconds. But what we've got here is a map. So we've got a key. The key is represented in binary in this case, and it just maps into some values. And kind of like a classic append-only log, this is verifiable. We've given a short witness. We can prove that whether a particular key and value is currently present in the log or currently missing from the log. And maybe one other observation is that this log is clustered by prefix. So as we add new entries to this log, entries with the same kind of key prefix live together. What are we going to put into a log that looks like this? Well, we're going to put domain names, obviously. And those domain names we're going to do in a reverse order, so from .co.uk.com down to the effective top-level domain, like bbc.co.uk, and then all the way down to the subdomains. And now you can't actually do this in a KT system, because this would, in a KT system, you need to protect the key. The key is the user identity, and you need to protect that. But in the public world of CT, we can use these structured keys. And this is going to give us some really nice properties later, because all the subdomains for a particular website are typically of interest to one person. And now they're going to share a path to the root, which is going to make their audit proofs much smaller. Again, not something that we can do in KT, but something we can do now that we've removed that privacy requirement. The next question we've got our keys, but what are we going to put in our leaf notes? And a answer for this, I'm not going to say that this is the right answer, but a answer for this is some kind of hash chain. So it's going to be some kind of witness of the current set of valid certificates, and it's going to link back to what the previous set of valid certificates was. And that's going to give us, together, this kind of jellyfish-like structure, where we have this tree on top, which is mapping from a particular domain to a particular set of valid certificates. And then each individual leaf node is going to record the history of the keys that were valid for that particular domain. And we can do some pretty neat stuff with this. So in the world of certificate transparency, we have revocation. What if you've issued a certificate and it was bad? Well, we can maintain this as a structural invariant in our tree. Whatever the latest certificate set is, we will define that to be the unrevoked certificates. And whenever we see that a certificate gets revoked, we're going to want to update this set to remove an element. And that will then move down the rest of the chain in the rest of the history. The second thing we can do is that currently, logs tend to grow forever, but maybe we would like to gracefully expire entries from our logs when we no longer care about them. And with a hash chain, we can do that very neatly. We can simply eliminate the oldest part of a tree beyond a certain timestamp. We can delete it. We don't even have to update or mutate the tree to do so. It's still verifiable from top all the way down to that particular timestamp. And with this kind of structure, you get a really efficient kind of set of proof lengths, much, much better than what a KT system can deliver. To prove that a particular certificate is present in the system and not revoked, we're talking about something roughly in the order of log D, where D is all the effective TLDs. So that's the set of effective top-level domains. That's much, much smaller than, say, the number of certificates or the number of updates or the number of subdomains, which is pretty succinct. And we also have the property that if another site is, say, for example, has a huge number of subdomains, say, like GitHub Pages, for example, that nest of the subtree under GitHub Pages doesn't affect anybody else's path length. So like overall path lengths scale towards the size of the number of effective top-level domains, not the size of the number of domains. For website owners who are interested in that kind of end-to-end property, they're going to be looking at a set of domains and subdomains, which are all going to appear together within this tree, which means that their proofs can reuse the same path from, say, bbc.co.uk up to the root. And then below that point, they're typically going to be interested in like the full take, as it were, which is to say every certificate, every entry within a different time point within that. And this hash chain structure gives you that because you're interested in contiguous windows, and a hash chain gives you a very effective audit for those contiguous windows. In terms of a KT system, like plugging this into something like Parakeet that AKD or that Meta are using, you're typically looking at a tree size that scales with the total number of all certificates. And roughly proof lengths are about, just to do a simple, is this certificate present and not revoked? You're looking about 3 times log the total tree size. So much, much bigger in practice than what you can achieve with this kind of design with that privacy restriction removed. So this gives you this kind of cheap end-to-end proof that a client can verify that a particular certificate is present for that domain and it's not revoked. It gives you succinct proofs that all certificates issued for a given domain and its subdomains can be listed and enumerated and that none are missing. You can potentially have much lower egress costs for the logs because the logs need to serve the users, the website owners, but they're serving them succinct proofs, and website owners are only interested in a small part of the tree. And they still need to serve a full part of the tree to some auditors, to a quorum of auditors, but that can be a permission system which doesn't have to scale to like the public web. Well, depending on how you want to set up that ecosystem. And then in terms of storage costs, this log doesn't grow forever. It grows to the number of active certificates that you're retaining, or the active number of domains, not the total history size that you want. So potentially that gives you different trade-offs there as well. In conclusion, we've drawn some of the owl. I don't think anyone's going to go home and say, well, my God, that's finished and that's going to work. But I hope I've kind of persuaded you that there's some interesting KT-like applications here that might solve some challenges in the CT ecosystem. When we loosen that privacy constraint, that design space gets even richer and it allows for much more efficiency. And like the end goal that I would love to see us get to is where tools like CertBot can provide that end-to-end transparency. When you run your CertBot to get a new certificate, you also get that succinct audit proof about all the other certificates that issue for your domain in a way that you can check and monitor. Please do come say hi if this is of interest, or if you know prior art in this area, or if you've looked at this before. Thank you.
Can I get Jon to come set up while we take questions?
Hey, on related work, have you read the paper Verifiable Lightweight Monitoring for Certificate Transparency?
I don't know.
It basically is doing what you're describing here with regards to the monitoring, but slightly different, and only solving the monitoring problem and not doing the revocation. So okay. You might want to look at that.
That sounds great. Thank you. Yeah.
Have you given any thought about if this could also apply to binary transparency? You know, given if you can represent binaries by identifiers that could decompose into a tree, like if we talk about namespacing within ecosystems, I'm curious if there's kind of a direct application here.
Yeah, I would think there would be, and I had a brief thought about this before. I think the thing with CT is that we care about active, valid certificates, which pushes towards that hash chain where the top of the hash chain is always close to the root. But in a binary transparency world, I guess you care about all the old software versions, like the extended support and so on. So there you probably want something flatter, like a regular Merkle tree, or to continue to use the prefix tree at the top level. But yeah, I think there's some really interesting applications there as well.
Any more questions? We'll take one more.
So you said that we don't have a privacy concern here, but let's say we have this kind of tree with text prefixes, and we make a query to this tree. Aren't we leaking our browsing history effectively?
Yeah, so for website owners,
Yep.
we sort of trust that they don't really have privacy in the first place. They're on DNS. For clients, we would want someone else to give them that proof, right? We wouldn't want clients to have to go fetch it. And the website operator is well positioned to do that in, say, TLS, where they've already fetched this proof for you and they can provide it to you without you having to go look it up.
Right, thanks.
Great. Thank you very much. And let's have a round of applause for Dennis. Okay, now we have our final lightning talk and tackling multi-layer interoperability. Please welcome Jon.
Thanks, everybody. Just to give you some idea about me, I have two hats. I am the CTO of Data Trails. We provide transparency services commercially, but I'm also co-chair of an IETF working group working in this area, which is most of the topic of this talk. But to give you a different kind of better idea about me, here's a little section from some of my personal library and a section of the floor of my study. Just to sort of frame why I'm here and why this is interesting, and try and stimulate some conversation really for tomorrow, for the breakout sessions, for the socials, whatever else, about really what we're trying to achieve here and how we can help each other achieve it. So a couple of the things, especially when I started in this, which is as long ago as many of you, surveillance is kind of ubiquitous with transparency in some sense, particularly in classic literature. But to grossly misrepresent a quote from one of these books in particular, one of the takeaways from David Brin is that if you're worried about surveillance, then maybe the problem isn't that too many people have access to transparency and information, but too few. And actually, in order to fight back, if we can have reciprocal transparency and accountability, we'll be in a much better space. And what I'm trying to do really is to try and get transparency tech into as many places as possible, as many applications, as many areas as use data as we can. So remembering that, of course, again, grossly misrepresenting a quote from the Trillian docs, that transparency and transparency tech is really about being an observatory, not a policeman. We're not looking to prevent stuff from happening, but rather to expose things that are happening. So the way that we view transparency tech, it's generally useful. Anybody using data typically worries about these classes of problems, either backdating something, forging something, shredding something, or denying it ever happened when things go wrong. So in a sense, you could just have a single implementation of transparency and it would solve these problems. That would be great. Problem is, the details matter. And I hurriedly changed this slide because our keynote provided such a good set of examples of what the applications are. And interestingly, when you look through these things, supply chain attacks, so the kind of areas that I work in my company works in are as varied as tracking nuclear materials moving around to software transparency through all sorts of things, even AI models and data sets. It's all there, but they require us to make a whole ton of trade-offs, and those trade-offs go deep into the technology when it comes to operating at scale, when it comes to actually paying real money and real salaries to run them and things like that. So what are we going to do? Are we failing open or closed? Are we using privacy by design? And this is a really thorny one, because it's like in one case you want everybody to be accountable. In other cases you want absolutely no linkability between two attestation statements. I mean, how do you build that in a way that's defensible? We've got things like timeframes and long-lived things. We've got auditability. Again, big debates we've already heard about public versus private logs. Artifact availability is a huge one. So something that often comes through that I'm interested in solving and leaning on the combined wisdom of the room is, like, there's a huge difference between saying, I've got this thing, is it genuine? to searching a log saying, tell me everything you know that's genuine about some topic, to, well, I don't even know where to look. And all of these are valid use cases, but again, one true technology, one set of things, one implementation to answer all of those types of questions is just really hard. And then there's the topic of log replication, which again we've heard quite a lot about, and comes to the question of auditability, but it also comes to another set of trade-offs with, how quickly can I do this, how completely can I do this, how much does it cost the auditor to implement this thing versus the shipper or the service, which really begs the question, when people are looking at transparency technology or standards or implementation, you say, which one's better? And the answer is always, well, it depends what you're doing. It's my favorite version of the which one's better slide. Well, I don't know. You can pick which one you think is Tessera on there, but maybe it's the showroom. The showroom's probably the nicest thing in there, actually. So what we need, I think, is a bunch of building blocks to enable transparency systems to be built out of the best set of those trade-offs. And I think the sort of thing that I'm looking to do, especially with my standards hat on, and again, looking forward to the breakouts and the conversations tomorrow, is I think you always need more than one, but not very many options, just to hit that right set of trade-offs. So you can have the sort of really super privacy-oriented things, the really super scale-oriented things, the really super whatever cheap-oriented things, whatever it is. You know, a few options, but not that many. So one thing that I want to talk about and quickly introduce, I know some people in the room already know about this, but one significant option and a place where a lot of this thinking and work is being done is in the IETF. And note that it's not a massive curveball, because IETF Skit was actually imagined originally in part as an extension and a generalization of CT. So 9162 is the current CT version 2. And essentially what it designs is an architecture reasonably pluggable, building block based, scalable, where issuers can make statements about artifacts, might be an SBOM, might be a binary, might be a firmware, it doesn't matter. They put it in a nicely defined cryptographic envelope and then ship it off to a transparency service where it gets packaged up and put in a receipt. What that looks like in practice is you can put basically anything into a well-defined structure for what a statement is. It gets signed in some way, which is then well-defined and parsable. It then gets put onto the log, and what you get out of it in the end is what we call a transparent statement, which is exactly what we've seen a couple of times before earlier today, which is basically the statement with the signature with an inclusion proof, and a reasonably efficient compact inclusion proof that comes straight back to you so that you can hold it in your hands and then do whatever you like with it. But it means that you know that your thing is now on the log. And the benefits of these standards is that they're very small and compact, they're easy to handle. We've built one and it's quick. So all of these concepts we've heard and the things that already work and are implemented in CT and KT also work here in a general sense. And there's lots and lots of opportunity for interoperability. So there is code here as well, just to suggest it does actually work. And what I wanted to say on these particular highlights is just to pull out that this isn't like a brand new thing all its own either. This is based on all of those same building blocks that CT and others use, so it's all using COSI, CBOR structures, things like that. So it's built on the same base, it's using the same principles, just a place where we're applying the thinking on generalization and use case expansion. So where's the interoperability? Well, I think the interoperability opportunities are in every single one of these places, right? So even in the artifacts, you've got questions on things like SBOMs. That's a lingua franca, that's fine. Maybe we want to talk about things like that. I'm not so interested myself, but it's a thing to think about. But then definitely by the time you get to things like structuring the messages and having efficient parsers, when you get to things like the signatures, we have even simple issues like algorithm registries. So we've heard some very opinionated talks today about only having one suite. that's not going to be enough in the end. So when we look at expanding suites, how do we do that? Well, we've got a registry already in IETF, so let's use that. Then you've got the log formats. Hopefully Robin will be doing a lightning talk on Friday about log formats. But yeah, we've got all these questions about tiles versus Merkle mountain ranges versus flat logs. They all have their place. They all have their benefits. And picking the right one for your use case shouldn't mean that you lose the best of all those other things. Having it pluggable, having it interoperable just makes sense. And then finally, you've got these areas here with the replication, the verifiers, the auditors. I really liked the suggestion from the last talk that we could have all of our logs being monitored and published in an independent third-party service. Sounds great, let's do that. So all these questions of how do I achieve that and how do I get lots of people on board can only be easier if we agree some small number set of ways of doing this that just makes the adoption so much easier. We have the open source code that's so much easier, and it'll just happen better. So obviously there's loads more animals in the zoo. It's not just SCIT, it's not just IETF. There's a lot of work going on in ITU, C2PA, CAI, that sort of thing. There's obviously all of the OpenSSF. So there are lots and lots of places where this work could happen. But personally, I'm here with knowledge and interest in IETF SCIT, so if you guys do as well, or have any better ideas, please do have a chat in the halls. So, thanks very much.
Thank you, Jon. And we'll take a question. Okay, I really liked how the final lightning talk had a callback to the keynote, and that feels like a nice way to bookend it. Okay, let's give a big round of applause to all our lightning talk speakers, please. Yeah, we've now reached the end of day 1, so we look forward to folks joining us for day 2. But don't forget, there is an event today at Flight Club Islington. You can all join us with, and don't forget your waivers. But yeah, thank you very much for joining us, and thanks as well to all our speakers we've had today. I think they've been really fantastic and lots of food for thought for the next couple of days. So one final round of applause, and I'll let you go. Day 1 is done.